Good morning, everyone. I would like to start this session on time, maybe 13 seconds late. I'm Azra Bihorak. I'm a professor of medicine, surgery and anesthesiology at the University of Florida, and I have a privilege to co-chair with my colleague from Florida, from University of Miami. This is a session, Progress Through Artificial Intelligence. It's a long session. We will have blocks of 3 talks and then block of questions for these 3 talks. So please, for speakers, if you can stay, it would be great. If not, we understand if you have an overlapping commitment. And for audience, please bring your best questions, and I will have my colleague introduce herself.
Thank you, Azra. So yes, I'm Haley Gershengorn. I am also from Florida in the United States, although at University of Miami, and this is our first opportunity to meet each other, so the U.S. is large, as you guys know. And I have the privilege of inviting up our first speaker, Edward Schenck, who's coming to us from New York in the United States, and he'll be speaking on what do we want the machine to learn.
All right. Thanks very much to the chairwoman. I'm excited to come here. You know, I wanted to start the morning with potentially a provocative topic, hopefully to get us all thinking, as we're going to be hearing a lot of practical talks and potentially a little bit more direct, applicable talks in the near term. But I want to get us thinking. All right, so relevant disclosures that are not particularly interesting for this talk. However, I will say that I am not a computer scientist. I am a clinician, and I consider myself a little bit more of a philosopher of medicine. And so hopefully I can bring a unique perspective on what we're talking about today. So let's start with how machines think, because if we understand how they think, we can understand what we want them to learn. And so on the left-hand side of the screen here, you can see, features in a kind of dimensional space where we have different axes that are relative to the value of those features. So think of things like blood pressure that can have high or low values. You add on different features in their relationship in different dimensions. And when you take multi-dimensional spaces like this, what a machine will do is can make a prediction knowing some of these values about what the other values are. And this is generally when there's a labeled outcome, such as like a mortality or sepsis, et cetera. This is supervised learning, and this is basically a predictive algorithm. Generative AI uses prediction within a context window of how tokens or different features go together, so that it can predict what an output based on those tokens would be. Other applications of machine learning include description, where all of the features are unlabeled, and we can see how they fit together naturally without our input. So that's just a basic overview of what we're describing here. AI models perform better with more processing speed, data, and parameters. So this is the figure from the OpenAI's comment on the scaling laws from before. So this is compute and data set size and parameters. So the more, the better. And I just want us to keep that in mind as we're going through all of our talks today. And this is a paper from a few years ago, the bite to bedside gap in intensive care medicine, that goes over the landscape of AI in the ICU, and specifically most of what our output so far is predicting complications, predicting mortality, improving prognostic models. And these are predictive AI, and they often fall under the landscape of clinical decision support, or some way to help us think going forward about what might come next in the ICU. A specific example of a successful clinical decision support is the TRUES system, or Targeted Real-Time Early Warning Score, out of Johns Hopkins, which was developed out of multiple features within the medical record, including scores and scales like Glasgow Coma Scale, the SOFA score, but also kind of documented tabular data such as the International Classification of Disease-Based Chronic Disease Threshold, together with flow sheet data like temperature, respiratory rate, different lab values. And this generates a score. You can see on the right-hand side of the screen. This generates a score that will pass a threshold and alert clinicians that septic shock might be coming. But I neglected to say here that despite all of this research on these clinical decision support, most of these are not actually been supported by randomized clinical trials and are not in practice. And despite the fact that this was 4 years ago, the literature is still the same. And so I like to think of this as we are at the chasm of implementation of we are developing a lot of AI models, but we have not figured out how to cross the chasm into mainstream use. And one of the later talks today will be given by Michael Pinsky, and they recently put out a AI workforce development position piece in critical care that highlights all of the different challenges when developing clinical decision support and how we might be thinking about those challenges on from planning to data quality to model development into implementation challenges. But what I want to focus on is the data quality piece. And what I mean by data quality specifically is just one component of that, and that includes tabular data, which are generally codes, scales, and syndromes. So data that's not continuously measured, such as ECG tracings or high-frequency physiologic data. And so I'm inspired by people from the past. This is Roger Bone, one of the grandfathers of sepsis development. I love this quote: "Poets may struggle for centuries to measure love. Physicians do not have that luxury when it comes to measuring life in the ICU." And let's take a little bit of a different direction here with how our medical record has evolved. So this goes back even further from Dr. Bone's comment here. This is Larry Weed, who is an evangelist to the move from the source-oriented medical record to the problem-oriented medical record, which took the idea of international classification of disease, which is an even older concept, so the systematized classification of diseases like tuberculosis or pneumococcal pneumonia, et cetera, and added onto this concept the idea of problems and organized the medical record around the idea of problems. And so I'm going to give you an example of what a source-oriented medical record, which is the old school way of doing things, to the problem-oriented medical record in a little bit of a glib comment. But this is a patient story, a 53-year-old with diabetes, seriously ill with a T-cell lymphoma, aggressively treated with traditional cytotoxic chemotherapy that did not control his disease. This was followed by targeted antibody that also did not control his disease. Over the past few weeks, he's been critically ill with multi-system organ involvement from his lymphoma and several infectious complications. He's now undergoing salvage cytotoxic chemotherapies complicated by polymicrobial bacteremia, including Klebsiella in Canada. Most recently, his shock has partially responded. Total vasopressor dose has decreased from 1.5 micrograms per kilogram per minute of norepinephrine equivalent to 0.2 micrograms per kilogram per minute. His urine output has improved, event support has decreased. However, so this is my take on a source-oriented medical record. It tells a coherent story, and we all can have a clear picture of what's happening with the patient and what the potential pain points and problems might be. Here's the attending version of the same story. Acute metabolic encephalopathy, I have no idea what that means. Acute hypoxic respiratory failure, sinus tachycardia. Is that a problem? I thought or what is this? Septic shock due to Klebsiella pneumonia, why is that fourth on the list? Fungemia, isn't that related to the septic shock? I'm not understanding why it's a separate problem. AKI, lactic acidosis, hypocalcemia. This goes on and on. So there's also a notation for transaminitis, steroid-induced hyperglycemia. Are you sure it's from the steroids? Ileus T-cell lymphoma is now 9 on the list, even though the patient would not be in the ICU if not for the T-cell lymphoma. Immunocompromised due to chemotherapy, pancytopenia, overweight, and severe protein calorie malnutrition. No matter how many times I read it, I don't know what that means. And so this is accelerated, at least in the ICU. There's this Health Level 7 is a company that has helped push this onto unsuspecting documentation improvement kind of industry within the healthcare setting in the United States. This fast healthcare interoperability resource standard. So this idea that you can create standardized terminology to describe the human condition, such as without transportation is a standardized problem, susceptibility to falls, exposure to communicable disease, that's a separate problem that you have to kind of list out. A fear of cancer is a problem. All right, so that's where the problem-oriented medical record has brought us. Let's talk a little bit about scales. So scales such as GCS or the the kind of injury severity scale in the trauma literature. GCS has been documented for over 50 years, and we intuitively know what a GCS of 15 is now. If you're a practicing physician in the ICU, we know what a 13 is, we know what an 8 is, we know what a 3 is. Similarly, in the trauma world, they know what an injury severity score means, an implication for how rapidly you have to take someone to the OR, et cetera. And then we have syndromes. So this is the first documentation of a consensus definition of ARDS going back to the 1980s. And in the early 90s, we also have the consensus definitions for sepsis. And what these are kind of plucked out of arbitrary thresholds of PF ratios, 300 for ARDS, it used to be lung injury, now it's mild ARDS, et cetera. Sepsis based on, the systemic inflammatory response syndrome thresholds, which are arbitrarily chosen out of expert consensus. And these have been updated, of course, but they remain arbitrary definitions. And so the current state of affairs is we take clinical data, we process it into a manually curated pipeline into formal data standards. So doctors are the digitizer. So clinicians take the human condition and we transform it into this pseudo-digital representation of disease. And we create this thing called the electronic billing research record. I threw in the billing there because that's really what it's designed for. And we use systemic definitions of disease that require yes or no labels, whereas in reality, everything is a shade of gray. We use problems with diverse pathologic mechanisms, and these are now conflated with actual diseases. Syndromes are defined by arbitrary static thresholds, and scales and scoring systems are optimized for our thinking. I know what to do with a GCS of 3, et cetera, about disease and prognosis. And very quickly, let's see how this would play out. A young woman with traumatic brain injury, high fevers, lethargy, influenza on a nasal PCR, tachypnic, tachycardic, and hypoxic. Treated with high-flow nasal cannula, remains hypoxic. Chest X-ray is clear. Does the patient have pneumonia? Just as a little bit of a rhetorical question, but it's something to think about. And as we think about all of these kind of arbitrary labels, and what biologic process is the TRUES actually modeling when it's predicting sepsis? Sepsis was defined by sepsis 2 criteria with different thresholds and definitions. Sepsis 3 is now different threshold and different kind of concepts. However, there's so much more data available in the AHR, there's natural language. So let's wrap up the fellows version of that story. Of the patient with lymphoma, in medium-term prognosis, although grim, hinges on whether the recent round of cytotoxic chemotherapy has a durable enough response for the patient's metabolic and immune system to recover sufficiently to allow for a transition from critical illness to convalescence. Patient, family, and staff are committed to ongoing critical care until the effect of his recent disease-targeted therapy is clear. So we have an opportunity now because language models, so generative AI, can actually transform free text inputs into FHIR ready resources. This is an example during the last year of off-the-shelf and fine-tuned GPT models and Llama, et cetera, from different companies in the world to kind of mimic what would happen in this pseudo-digitalization that we currently are forcing clinicians to do. So I would say we're at a turning point. We can remain in the status quo in which we rely on the clinicians to do the digitizing, or we can potentially go to a different future, which might have different benefits. So the status quo is using clinicians to manually curate pipelines to create a formal data standard. You could also actually use large language models to pull data from the flow sheet to kind of auto-populate problem lists for the clinicians to annotate, which would be filling the medical record with language model derived output that is based on the pseudo-digitization. There's a problem with that. This is a provocative paper from Nature from last year, is that if you fill the record with language model-based output, you run the risk of models being trained on model-generated data, and then in a kind of recursive doom spiral, you end up getting probable events that are overestimated, that are fitted together. They poison reality, and improbable events are underestimated in a loop, leading to model collapse and less performance by your output. However, we don't have to use it this way. If we retain the clinician's documentation of free text, notes, and thought process, we can actually produce standardized medical output. So in the future, we could have, instead of clinicians operating under a formalized, rigid data structure in terms of the way that they document, we could preserve the narrative going forward and use language models to translate that into a standardized output. So I want to leave you with this concept that when we think about good artificial intelligence, this is a report from a survey of people in response to a hypothetical model telling people to extubate a patient with a complex medical condition, is that we want to think about the model's knowledge, medical knowledge, the knowledge in context, the model context, and the context of the patient-specific concepts of making decisions. So in summary, clinical decision support is largely based on concepts and structures that are not directly relevant to the human condition. It's largely by design and is related to our previous efforts to digitize medicine. Pseudo-digitization is changing the way we think about medicine. A renewed focus on the clinical art of natural language is possible. So how can we cross the chasm? To help the machine, we should do what we are good at, and that's tell stories. Thank you very much.
Thank you, Ed. We will take questions after the third speaker. So now I would like to introduce Dr. Matthieu Komorowski. He's from Imperial College of London. Matt is going to talk about challenges of moving from predictive to actionable AI.
Wonderful. Thanks, Ezra. Thank you so much. So moving from predictive to actionable AI is the topic of the next 15 minutes. These are my conflicts of interest. This talk came about after we co-wrote this paper with Jim Smith and Paul Elbers, actually, where we suggested this necessary shift from what is currently the bulk of the literature in AI applied to medicine, being predictive AI, into a new type of AI that would actually tell me, you, us, what to do if we want to impact the patient's trajectory and improve their outcomes. So it's not so much about an AI telling you, your patient has an 80% chance of developing sepsis in the next 12 hours. It's about an AI telling you, now is the time to start vasopressin. Now is the time to give a fluid bolus. Or you should change that dose of antibiotic because you're going to overdose the patient because they are developing a renal failure. And in my opinion, this is very much what we should be working towards. So let's dive a little bit into what actually is actionable AI and what's the underlying methodologies that could allow us to achieve this. So there's lots and lots of methods that potentially would work, but just to highlight two of them, I'm going to talk about behavior cloning and reinforcement learning, RL. In behavior cloning, it's actually very straightforward. You take some training data, a big data set of patient data and the treatment that was given to them, and you're going to build a supervised learning model to learn what dose was administered to these patients based on their characteristics. Right? So if you look on the left here, you have a bunch of patients, you have different doses of fluids and vasopressors where you're going to train a model to learn what dose they received. And then you can use that prospectively. In reinforcement learning now is different. You want to model the decision strategy and try to optimize it for a predefined reward. So for example, here you have different decisions, different doses given by different doctors to different patients, and you can, thanks to the framework of reinforcement learning, you can quantify the value of each of those decisions, again for a pre-specified reward. Reinforcement learning, just to give you a bit of intuition, picture a rat in a maze, and the rat is the agent of reinforcement learning. They can be in different states. In each state, they need to make a decision in order to transition to better states, and eventually accumulate reward and avoid penalties. And if you allow me this very crude shortcut, it's not that different from what we do in healthcare. We have our patients, and they're in different states of health or disease, and we want to influence their probability of transitioning to healthier states, and then to go home alive. or to recover from organ failure. So the framework of reinforcement learning is very much amenable to this sequential decision process nature of treatment. And then if you want to use those models prospectively, you have behavior cloning. Now you have a new patient coming in, you input their data into the AI, and the AI will tell you, well, in the training data, doctors would have given 100 ml of fluid to this patient. In reinforcement learning, it's very different. You enter this data into the model tells you this patient belongs to this part of the state space. In this part of the state space, the most optimal action to maximize the reward is going to be maybe decision B, is going to be maybe start a bit of NORAD now. So you're diverging from the behavior of doctors that was used at the time of training. And here I give you a few examples of what algorithms could allow you to do this. Okay, pros and cons of both approaches. Behavior cloning is actually very easy to train, very easy to evaluate. You just have to, you know the ground truth. The ground truth is what doctors did. You just have to measure, you just have to minimize the difference between what the model says and the ground truth. It's a classic supervised learning method. The problem is, or the limitation is that at best it will perform as good as a human doctor. And I would argue that very, very often we're not optimal. I'm not optimal, I know that. Reinforcement learning, the exciting thing is that it may perform better than the average doctor. It may perform better than the best doctor. That's the promise. The challenge is that it's hard to validate. It's hard to guarantee the safety of those models, especially, well, I'm going to tell you why. How can we validate reinforcement learning? The challenge is that in healthcare, we cannot afford to learn by trial and error. We call this being limited to the offline setting. We use batches of retrospective data to train an AI. In the field of computer science, they produce beautiful papers like this one. The first paper really bringing reinforcement learning and deep reinforcement learning to the forefront of the literature. 2015 in Nature, they trained an AI to play Atari video games without teaching any rules, pixel to action. But it took millions of hours of simulating gameplay. We cannot do this in healthcare, right? This little startup was, because of this paper, acquired by Google for £400 million, and it became DeepMind. So in healthcare, what we have time series of data. At some point, the patient develops sepsis, and then when you train your model, you end up with this. You know what the humans did. They gave some fluids at some point, at some dose, and the AI says do something different. Same thing for vasopressors, right? The humans gave a bit of vasopressors a bit later on. Maybe your AI says, well, start NORAD straight away. Now, how do you validate this? It is challenging. No method currently is perfect. But nevertheless, there's been quite a few publications demonstrating the promises of using reinforcement learning in healthcare in the last 5 years, let's say. So, for example, for this was timing of renal replacement therapy. This is insulin in diabetes, mechanical ventilation, steroids, antibiotic dosing. This is fluids and vasopressors, and even outside of the ICU, of course, right? It's not limited to the ICU. And yesterday we heard about this new beautiful paper on vasopressin, just published in JAMA. So all these papers are retrospective. None of them has tested the AI prospectively. So I want to tell you how I'm trying to do this in my own lab, in my own research. So first of all, it's a highly multidisciplinary teamwork. And you see here a picture of just some of the people involved. It's not everybody. But we have machine learning experts, we have software developers, obviously clinicians, human factors, health economics, medical device development, patient and public representatives, obviously the hospital research informatics, they're absolutely key. And what we do, we have a sort of a pipeline in our head where we push a model down this pipeline, and along the way, the studies becomes more and more representative of reality, but more and more dangerous. And we only move to the next step when we're satisfied. So just a few papers. This was the initial proof of concept. Now we have a number of new models that are improved from this initial proof of concept. And then we've done in silico simulation studies. Here are two papers. This one has a sort of a human factors twist to it. So this was in silico simulation study. Then physical simulation study, I'm going to show you what it looked like, but two papers recently on safety evaluation in a physical simulation environment. And more recently, I just completed the recruitment of patients and doctors into prospective studies in a shadow mode environment, meaning not at the bedside, and then another one at the bedside. So the physical simulation study looked like this. We invited doctors to come to this ICU simulation suite. This is not a real patient, it's a mannequin. And we presented them with a simulated ward round. 6 patients. We showed them the output of an AI on this big TV, and then randomly we injected unsafe AI suggestions to see whether they would be able to detect those. And we also used eye tracking. So this gives you this kind of very cool video where the green dot is the forward-facing camera, and we know exactly where the doctor is looking. And when you run this, with QR codes on the scene, you can actually generate regions of interest across the area, and you can quantify exactly how much time the doctors are spending looking at different scenes or regions of interest in the scene. Right here, looking at the AI screen, you see the bedside monitor, and so on. So it gives you some sort of a proxy for attention. This is the hope with eye tracking. What did we find? First of all, huge variability in practice. We knew this, right? I don't make the same decisions at 2 a.m. and at 2 p.m. This is one way of proving that this is the case. You see the distribution of doses suggested by those study participants on the 6 patient scenarios. Huge variability. Sometimes they say 200 mils, sometimes 2,000 mils of fluids in the next hour. So that's another rationale for why we need AI. We need AI to narrow down this range of variability in practice. We need to shift behavior towards more optimal decisions. And reinforcement learning hopefully can help us do that. The results. So good news, the doctors were able to detect unsafe AI suggestions over 80% of the time. We also asked them whether they would ask for senior help. So if you combine both, I think 92% of the time, unsafe AI suggestions were detected or blocked or escalated to senior help, and they would not have been applied to the patient. The result on the eye tracking, basically we found no difference between safe and unsafe AI suggestions except for the time spent looking at the AI screen. When the suggestions were unsafe, the doctors spent a lot of time actually looking at the screen of the AI, trying to understand what was going on and see whether they were wrong, whether the AI was off. We didn't tell them that there were going to be unsafe AI suggestions, by the way. We also presented some explanations for what the AI was suggesting, and we found that they didn't care very much about those explanations, which is an interesting piece of result as well. Prospective studies. So the first thing to say is that it was technically very, very challenging to connect those models that are very data hungry to hospital IT systems in different hospitals. It took me about a year to plug in the tool that we developed at Imperial College into a UCL hospital, about 1 year of me figuring out how to do this. And then the data is highly multimodal in nature, right? It comes from the bedside monitor, from the labs, from the ventilator, from the dialysis machine, from the infusion pump. So there's a very high bar in terms of data requirements. Many hospitals would not be able to deploy this tool. And then the first experiment, which we call XP1, shadow mode, I brought doctors in the research office and I showed them the output of the AI on a computer. They were not on duty, and we asked them whether they thought the AI looked safe, looked acceptable, sort of a safety evaluation, sanity check. I wanted to say a sanity check. The second part is a bedside live pilot study. To my knowledge, it's the first time a reinforcement learning system is deployed live at the bedside of real patients with actual sepsis and shown to actual doctors looking after these patients. But it's not a randomized study. It was, again, a lot about the technical feasibility, and then, of course, we're doing a bit of safety assessment. So we're asking senior ICU doctors what they think about the output of the AI. Would they be happy if the AI was administering those drugs to the patients? I can't show you the results because we literally just finished the recruitment, but stay tuned, I would say. Conclusion and lessons learned. Well, this is hard, right? This is a full-time job for many people. Lots of technical challenges, as I said. You need high-quality data. You need a high-spec server. If the server is too slow, then you sit by the computer and you wait 4 minutes for the data to actually come from the database. Running the AI itself is not very heavy when the model is trained, but I could spend a long time talking about the technical challenges. Scalability obviously is an issue. I don't see this tool being manually plugged into every hospital in the world because that would be just impossible to do. So we have to think about technical solutions to enable scalability if this was to be the case in the future. Safety risks. We know there's heterogeneity of AI impact. Some doctors actually the AI might worsen the performance of some doctors. And this was, for example, shown here in AI in radiology. Some doctors made more mistake when they're shown an AI system. How much preliminary evidence is required before doing an RCT? That question is still up in the air. When are we going to be confident enough to actually tell doctors to follow the AI suggestion? And just final point, the importance of multidisciplinary teamwork and the importance, I would say, of trying to follow this structured, stepwise safety evaluation. Lots and lots of people to thank, obviously, in this work. I'm just here representing them. And I want to thank the funders and our study participants, of course. Thank you.
Thank you so much. And again, we'll have an opportunity for questions after this next speaker. So I have the privilege now of inviting up Paul Elbers, coming to us from Amsterdam, and he'll be speaking on Beyond ChatGPT, making large language models work for you.
Thank you so much for that kind introduction, and thank you all for being here. I think it's a very smart choice to be here because AI is definitely going to change your lives, and I'm going to tell you a little bit about how that is going to happen. It's also a very hard talk to give because this domain changes so fast. My talk could be outdated in the next hour, so that's a caveat. So I'm from Amsterdam UMC, from the Center for Critical Care Computational Intelligence. You might know the Center for the release of the Amsterdam UMC database, which is downloadable for free, so you can start doing your own research. As for conflicts of interest, I work with a scale-up company called PacMat, and I also do some machine learning for Fisher and Paykel, and academically I'm the current chair of the ESICM data science section. So this talk is going to be fast-paced, and it is based largely on a review paper that we were invited to submit to the Journal of Intensive Medicine on large language models in critical care. So if you want to read more about that, you can download that later. So when we're talking about ChatGPT, we can also talk about the many competitors and the many models that are currently being put out there. But bear in mind there are also a lot of medical foundation models that are specifically geared towards use in the medical domain and trained on medical data. So an important example is the one at the institution of our chair, the Gatortron in Florida. And just to give you some perspective, because all these large language models throw with numbers, so you need to remember that in the human brain we have about 100 trillion connections to each other. So how does that compare to the current state of the art of large language models? So as you can see, the human brain is still probably much more connected than even the largest large language model to date, which is, well, they don't really release all these numbers, but it's estimated that GPT-4 is now the biggest connected one. And maybe that is the reason that these large language models currently do not function at human tasks as well as humans could do. You might even say that they can be considered to have mild cognitive impairments. So in this interesting study, current large language models were asked to do a human test on assessing mild cognitive impairments, and they basically did not pass the bar of normal human functioning, right? So the authors there argued that these models are currently still cognitively impaired. However, these cognitively impaired models are able to do many things, such as pass the MBA exam, and pass law school examinations, or the USMLE, and recently even the Chinese critical care examination. So they actually did very, very well there. And as a former committee member of the European exam, so the European Diploma of Intensive Care, I don't know if I'm proud or a bit sad to say that these large language models now have also passed the European exam for intensive care medicine. So you can all go home now, right? So how does this affect your practice or your daily life today? So this is a bit of an older paper already. So 2023 should now be considered old, and this is by the former speaker Matthieu Komorowski. But he and at that time it was quite visionary, because the things he outlined are still quite true. But because today, if you just use your favorite large language model, but be a little bit careful about the privacy aspects, I'll come to that later. It's very easy to get fast and accurate information. So in green are some suggested actions you can ask them to do. And of course, for administrative tasks, it's already well known that large language models can help you greatly, or to enhance communication, to explain things in well, for example, like a 5-year-old, or for medical education. And as many authors of scientific papers have noticed, it is really great to help you in scientific writing, although of course you should always take full responsibility of what you write. So it's a natural bridge to prompting techniques. So if you want to read more about it, this is a review on how to optimize your prompting techniques for the medical domain. But bear in mind that this is also a very fast evolving science. So what you read here might already be outdated tomorrow. But here are some examples. So the most simple thing you can do is do direct prompting. So for example, what are the latest sepsis management guidelines? But it's probably better to have your large language model to assume a role. So for example, telling them you are an ICU consultant, so how would you explain ventilator settings to a junior doctor? Or tell me more about CRT in a septic shock patient. Now taking that one step further, you get to few shot prompting. So it's basically given an example in your prompt on the type of output you want to have. So for example, here are 2 examples of ICU discharge summaries, and you need to give them, of course, anonymized, right? Because all these companies will use your data, which, depending on your perspective, is a good thing or a bad thing. And you can generate a similar summary, the large language model will follow those examples. Taking that even further, you can go into self-reflective problems. So you're basically asking them, for example, to explain permissive hypercapnia as tolerated in the RDS, and then challenge that explanation by discussing potential risks. So you're forcing the model to rethink the answer. And that brings us closer to the so-called chain of thought prompting, in which you're really trying to seduce the model to use their reasoning capabilities. Now, these have led to the development of reasoning models, such as GPT-01, which basically have that built in. So they are using a reinforcement learned technique to incorporate that reasoning capability. And you can think of those models as a senior coworker, so you can give them a goal and trust them to work out the details, whereas your bread and butter GPT model would be more like a junior coworker. But that also means that you should use different prompting for either of them, right? So for the senior model, you don't need those reasoning prompts. You can just give them very simple tasks, but they will do the reasoning strategy for you. You can read more about that, for example, at the OpenAI cookbook. So I think that large language models for medicine, and especially for intensive care medicine, should be viewed as reviewers, companions, or a second set of eyes. And what is going to make this really awesome is the concept of retrieval augmented generation, so RAGs. So what that means is that we do not only have the large language model as it is, but we also put documents, and these can be a large number of documents, for example, your local guidelines or protocols, to enhance that knowledge because the language model will retrieve chunks from that external knowledge base that you can put into that through semantic similarity calculations and take that into account with the answer. So that looks something like this. So in the right upper corner, you can see that these documents that you put into that are first indexed, factorized, and embedded. And then in the chain of thought and in the chain of from prompting to answer, they're considered by the large language models, and the answer is basically a combination of what is in the foundation model and augmented by information in those documents. So there's really a lot that can be done with this. So for example, you could use it for academic conference organizations, such as this one. You could use it for biomedical literature recommendations. We could enhance our systematic literature reviews, and we could also even create living systematic reviews that are continuously updated, so there's no need for reviews anymore. We could use it for screening for trials, so this works really well, right? So you see that the AI identifies people eligible for trials much earlier, and also a lot larger number of patients could be enrolled in this trial from these examples. And we could also use it to do fully automated research. So the AI would generate the question, generate a hypothesis, analyze the data, and answer the question and write a paper for you. And then we can all go home. So currently it can already be used for more efficient reporting of hospital quality measures. So for example, if you need to report for your registry, was severe sepsis present, yes or no, you can use a large language model for that. Although I must say that this still suffers from some hallucinations, so you want to be careful. There have been some attempts to use large language models to predict outcomes, such as after cardiac arrest. Bit of a warning here, but they do better than traditional legacy predictive models. And a well-known application is using large language models to respond to a lot of patient messages in the electronic health record. Has been submitted to trials. I must say, that doesn't really work as intended, because it also induces some harm in those messages because of hallucinations, and it also didn't really increase the time spent. I mean, it didn't really free up any time, because it actually increased the read time with no change in reply time. For intensive care medicine, specifically in Ireland, they have used it to assess the usefulness to summarize medical notes. And I think what's coming to you, and there's a lot of companies involved in this, is ambient listening and also talking back to you. So, and now that recently Microsoft has entered the arena with the Dragon Copilot, you'll probably see that incorporated in lots of electronic health records, although it's likely going to be expensive, I would say. So, the holy grail is, of course, trying to train large language models to do some diagnosing for us. And I mean, you've probably tried it, right? They're actually pretty good at it. At least that's my opinion, especially when it comes to rare and complex diagnoses that you don't encounter frequently. And that brings us to the question, is generative AI capable of clinical reasoning? So if you look at the technical backbone of it, so you would argue no, right? Because it's just basically a probabilistic determination of what the next word is going to be, right? But on the other hand, the way the systems are designed now, and this is not a picture of how AI works. This is a scheme of how the human brain works when making diagnosis. And but it looks very similar to the schemes that I've shown you. So I would argue that LLMs do hallucinate and augment biases. So you need to be aware of that. They do mostly rely on text, but yeah, depending on your definition of reasoning and the way you measure that, I think LLMs will at least exhibit superhuman performance on those tests. Whether that is reasoning or not, you can debate, but they will be better at it than you are, or at least better than I am. So, this has recently been tested in a trial. I think it was February, instructing clinicians to look at cases. And these were cases from the podcast Gray Matters of, it's internal medicine, right? So probably difficult cases. And as these cases they were adapted for the study, they were not available for GPT-4, and also, of course, not for the participants. So they randomized 92 physicians, and they instructed them to either solve the case with the help of GPT-4 or without GPT-4, but with whatever other support like Google or UpToDate. And yeah, I mean, it's probably no surprise, but they were better when they used the large language model. But the large language model alone, without the physicians, was doing equally well. Although the spread was a little, I mean, the best physicians plus GPT-4 were still better than GPT alone, right? So that's kind of reassuring. Interestingly, they spent a lot more. It took more time, right? It didn't really save them any time. It took more time to solve the case, but the net benefit is probably that the cases were solved more often. So I will conclude now by warning you a little bit that there are also some risks involved in using these large language models. And this is a peer review of the technical report. And what it basically says is be careful out there. So we've already talked about hallucinations, but there can also be harmful content. You have to be aware that the biases that are aware in our medical electronic health records, whether they are racial or sexist, they will be perpetuated in these large language models. It's also very, very scary that there is an oligopoly in these large language models. So the amount of funding that is needed is not available for single hospitals. It's probably reasonable to say that nations and continents and governments could probably do that, but there's really no incentive. And so therefore you want to really take care about privacy issues. And also these training of large language models costs a lot of money, but also a lot of water. So I just want to highlight two more things. That's actually a funny story about the representation of intensive race and ethnicity, how this is depicted by the current image generation models. So you can judge for yourself. There's probably some bias in here. And it's also good to be aware of the fact that we are now at risk of data poisoning attacks. So the good news is if that is depressing to you, then you can just now talk to a large language model to solve your depression. But seriously, we need governance and we need education. That's the only solution. So in terms of governance, we need transparency, safety, and ethics, model lifecycle control, and in education, we need conceptual AI instead of programming for all intensivists. Indication and contraindication of AI models should be known to all of us, and we should be able to interpret and appraise published models. So you started doing that by coming to this session. It's a very good start, and I would like to end and encourage you to learn more. And with that, I thank you very much.
Thank you, Paul. We'll take questions now. We have 15 minutes, maybe a little less for questions. Any questions from audience. Do we have a micro? We have one question there. A microphone is coming behind your back. Here's on the right side, to the left.
Good morning. Thank you for the very good presentation. Steve Haynes, I'm an intensivist in Worcester in the UK. How do we work out whether the answer we're getting back from whatever computer system we're using is accurate? To give an example, not that long ago, within the last 12 months, I actually asked ChatGPT the really complicated question of what are the constituents of Hartman's solution, and it was not right. The answer was incorrect. So given such a simple question, and it was incorrect, on very complex issues, how are we going to know whether the answer we're getting back is correct?
Yeah, so there's a number of good points you raised. So a simple answer could be that you want to try better prompting, right? So you want to revise your prompting strategy to make your model think better and revise the answers, or use the better reasoning models. The other point that I have, I mean, for the simple question, you would know it, right? But for the more complex questions, you would maybe also ask a colleague if you don't know your question, the answer to your question, and then I would ask you, how would you know your colleague is right? Huh? And then there's, and I think you should see large language models or AI in general as these progress to more mature solutions, as a colleague that you ask questions and that you either trust or don't trust. So why do you trust your colleague? And you might trust some colleagues more than others. It's because you have the experience that their answers are usually right. So it's basically you need to play with the answers and try to optimize your questions, and then get a feel for when it's wrong or when it's right. So then you build the trust relationship with your model, just as you would do with your colleagues. Whether or not that will never lead to wrong answers, well, it's very hard to tell. There probably will be wrong answers. But I think the real question is the frequency of wrong answers from AI when these models develop, is it higher or lower than the best of your colleague doctor?
I just wanted to make one comment also, that there are some versions of language models that incorporate pulling references that were help them generate the textual outputs. I don't want to specify which one or push which one, but there are some that allow you to do a trust but verify sort of approach, that if you're interested in the context of the output, you can follow links to see the source documents, which I imagine would matter with the reinforcement learning and the explanations there.
I saw a good example in the news about reversal RAG, I think it's called, where actually the model goes back for every statement, goes back to the source document, the source link, and can provide basically reassurance that the statement are as accurate as possible, provided there's a reference.
Was there another question? You saw it. I can ask a question. I guess I'll take the prerogative. So I loved the fact that we went everywhere from starting with we're stuck at this chasm where we're not necessarily adopting these, to we really need to be smart about how we study the impact we're going to have, to, hey, look, these are all the tools that we have available. And I really worry for me, and I therefore think for my clinical colleagues, when we think about the new study that came out in JAMA that was presented yesterday, people are going to read it and be excited about it, and these models are going to find a way into our systems, maybe before they've had some of the study that your group is doing. And I'm wondering how you guys feel about that. I've seen that with predictive AI already, right? The companies sort of pushing them on us, and our hospitals being on board with them because they seem like simple solutions. And I'm just wondering how you guys think about how we do this smartly so that we don't end up with those problems.
Question for Paul.
So I'm an AI optimist, right? So I think that we should embrace the possibilities, but we should also be very mindful about the possible downsides, right? So for me, that means that while it's good to be an early adopter, we should also try as a community to demand that there are results shown in terms of outcomes that matter to our patients, right? So we need, so even though these models are very are developed with very different statistical strategies than we are used to, the actual trials, they're basically, in my view, they should be the trials that we are used to. So just randomized clinical trials with normal clinical endpoints. And so there's probably going to be a huge push from the industry to already adopt them, like we have seen with other technologies. But I think as clinicians, we owe it to our patients that it will be ultimately proven that they do something for our patients. And then I will talk more about that in a later talk. But I think we should try to go to either shared revenue models with the industry, or try to only pay if it improves our patient outcomes, and not so much only pay for the product.
I also have a question for all three of you. So I am also optimist, but I'm going to be a skeptic now with my question. So, all what we are doing here, we are recirculating our words, and we are recirculating information contained in limited data, really limited biological data. We're not going very deep in ICU. We don't do imaging much. We don't go on tissue level, molecular level. So now, so we can optimize, obviously. It's a complex system we work in. We can optimize our decision. I can see that in a closed-loop system, that machine will be better, administering insulin or tuning a ventilator. There is no question about it. However, I'm worried that we're going to take attention and resources away from real questions, go deep in biology, understanding what disease we are studying, finding new therapies. We need new therapies beyond what we have. This is where I'm worried. So how do you think we can keep this healthy balance in, optimizing these decisions, but at the same time focusing really understanding our diseases better and finding new therapies?
I can take I agree with you. and that a lot of the worry about when you turn over the variability that humans produce within their varied clinical reasoning, although it might not be optimal for each patient in each scenario, that variability produces a lot of the ideas and the hypotheses that do push medicine forward, because we make mistakes, and some of our best output comes from the mistakes that we are making. And so sometimes if we turn over that variability to a model generation, then if we are stuck with what is optimal today, we might not learn what is optimal tomorrow. So I agree with you.
Exactly.
Maybe there's a different perspective.
Thank you. That's okay. Oh, two more questions.
So I'd like to respond to the two questions that were asked. With regards to research, a lot of the research that we generate, whether we realize that we're doing it, is basically structured on the Bradford-Hill criteria. So I believe that if we can take the Bradford-Hill criteria and somehow impute the concept into those tools that we're using, we might be able in the future, and I'm not saying it's the near future, I think it's a far future, to be able to have enough creativity without endangering our patients in terms of research. I won't be talking about that in the afternoon, so just a thought. And the second thing, in terms of safety, and somebody asked about that here today, I think that we, those that are optimistic are still very optimistic. I won't be talking about this either today, but part of my work is checking the outputs generated by a large language model. And I can tell you that the amount of potential damage caused by misquotations, wrong citations, even when they are presented to you. If you go into the quotation, into the paper, and you look, it's called I believe, faithfulness. That is the term in AI. If you look at the amount of faithfulness of the citation to the origin, even the paper exists, you're going to find that there's a lot of non-faithfulness, let's call it that way. So be very careful as you're using these tools. I think that you're absolutely right. We're getting them a bit shoved down our throats. And I will be showing how it's happening in my talk.
Thank you, Sharon. Thank you.
Was there another hand I thought I had seen?
There is there was one person.
It's hard, sorry guys, it's hard to see from up here.
No worries. Thank you very much. Excellent talk. Very enlightening. A little bit scaring. I'm a optimist on the AI side, but just because I think my usual lifespan on this planet will be gone before the machines take over. But I have a rather practical question. So I think the ultimate goal will be the clinical application into clinical practice of all these AI technologies. And one of the typical issues that we have in medicine is blame if something goes wrong. So I reveal I'm a surgeon by training, so with the anesthetist on the other side, we have this constant dialogue if a patient becomes hypotensive. Now this can go further, and one of the industries benefiting from the medical industry is the legal industry, suing us if something goes wrong. So from a governance perspective, how do you see what would be the appropriate measures to put in place when we start implementing these models into clinical practice? Because it's very easy for the doctor to say, sorry, not my decision, it was Dr. Chet. And the company who provides Dr. Chet said, well, we just provided a suggestion, so we don't take responsibility. Do you have any thoughts on this way forward, how to implement these models into clinical practice?
Yeah, I mean, I gave you the answer from as a developer of this technology. So far, the simple answer is we leave the liability on the side of the doctors. We say we provide this as a decision support tool, right? This is augmented information. This is a smart way of summarizing the information of your patient and providing some projections about what might be what you might want to consider as a decision, and then the decision is on you. Over time, if we project ourselves a few years in the future, I hope, as an optimist as well, that we'll have evidence that those systems actually do what they're intended for most of the time, that they are uncertainty, that there's some uncertainty awareness, that they have a confidence interval that is reliable, and then at some point there might be an argument that the balance is going to flip, in the sense that if you don't use those tools when they're known to be better than the average doctor, then you might be liable. So I don't know if, my goal is to help patients, right? It's not to make doctors feel good necessarily. And so whatever tool is best to advance the field of medicine, I think that's what we should be open to working with.
I can comment on that. According to, I work with a group of attorneys who are in the U.S. at least, who are experts on privacy and copyrights and all of that. And like in one bleak session that I attended, was told that doctor is always liable, at least in the US. It's always doctor. It's going to be mainly liability on physicians. And also, when it comes to copyright or intellectual property containing your data, because you may create it, as a pathologist, you did 20 years of job and you were paid to do your job, and you annotate every image, and then someone's give that data away, train the model, and then model learn from your expertise, like your intellectual investment, does it really exist? I hear that question all the time from pathologists. Where is the value, what I put in? And pretty much I was told, it's gone. Once they have it, it's gone. But, and the advice I got from them is copyright everything you have, copyright your data. That's the only thing you can protect yourself. So this is advice I'm sharing with you.
I think so. Yeah. Oh, there is actually a question in the back.
Good morning, thank you. I have a question regarding using AI in clinical practice, mainly for diagnostics challenges. I think we implement in our way of thinking implicit data and contextual data that are hard to put in the patient's file. Like last week, a nursing student came to me in the morning saying the patient had mottling. Came in the room, window wouldn't close. It was freezing, it's normal. Case closed. But nowhere in the patient's file, this is written nowhere in the patient's file. And in her monitoring file, it says mottling stage 3, mottling stage 3, mottling stage 3 for 6 hours. how do we close this gap? How do we say to the machines the thing that we, as living beings, integrate most of the time implicitly, or sometimes even unconsciously?
Yeah, so my take on that, first of all, spot on, because that is an issue. And the idea that large language models or any AI can be as good as humans will only happen when they can avail of the same armamentarium of sensoric information, right? But I think we'll get there, but not in the next month, but maybe in the next years to come. That's and we've seen experiments from that in China a lot, but also in the States, that we will integrate video and smell and tactility into these models, and then I would expect that they could be on par with human performance or even exceed that. But until then, you should still rely on yourself.
All right, I'm going to thank our first three speakers and all the questions you guys had, and ask for our next speaker to come up. So although she has already spoken to us, I have the privilege of presenting now Sharon Einav, and she's coming to us from Tel Aviv in Israel, and she'll be speaking on how it will improve clinical practice and research.
Right. So once I've overcome this technology of moving the slides forward, this is a bit of an optimistic talk, and since it's in Brussels and not in the States, I'm going to afford to actually be showing some sources that were not and are not that are freely available online. But so my conflict, I'm going to be talking mainly about practice, because research is a whole completely different topic. I was expected in 15 minutes to talk about both. My conflict of interest, as I mentioned, is one of my, it's not a workplace, it's sort of a consultation. I consult for an AI company, a high-tech company that's developing a large language model for medicine. And it's not on the market, so I can still be here. And there are multiple opportunities for us in intensive care in the future, and I'm saying in the future. And I'll start with first contact, because I think that's the first place that we will see our patient. And differently from my colleagues, I can tell you that there are companies already looking at, remember that patient when you come into the ED and then you get called in unnecessarily to see him, or the cardiologist should have been seeing that patient, or maybe you're sort of debating with yourself whether to call the neurosurgeon or the neurologist in this case. So here's this AI that's being developed that works exactly on this idea of how and who to refer to in order to decrease the amount of mistakes that are made in terms of referral, and therefore decrease the manpower that's invested in this sort of redundant specialist consultation. It can be done in the ED, it can be used outpatient, wherever. So I'm not selling this. I have nothing in the market, unfortunately. Imaging. My next point is imaging. I'm just going to touch upon each point. So here, for example, you can see a tool that looks at a implementation of time, the time it takes to diagnose anything that needs intervention. Okay, and here you can see a reduction by 11.2 minutes. Let me tell you, just you may be interested to know that our hospital administrator, I think about 15 years ago, decided that anesthesiologists are very, very expensive. They put somebody outside, this is a true story, to time us how much time do we go to the loo. And an anesthesiologist wastes more than 10 minutes a day in that important place. And this could save the same amount of time and allow us to actually go to this place. So I'm being a little bit cynical, but this is how our administrators are going to be seeing these tools in the future. So here is one, and there are more than 200 papers at this time showing similar work with this type of study. Here's another one talking about the time to acquisition with MRI. You know, it's very unpleasant in that sort of closed-in place. And we know we have an issue, for example, with breath holds, both in CT and MRI, where you sometimes have to disconnect the ventilator or put a PEEP valve, whatever, or hold, you know, your local ventilator. So, and you can see that here there are actual tools that are being used at. Some of these are still not yet published. Here's another one. This is, I'm not going to show you the movie, but you can all go into it online. This is something that's being developed in one of the hospitals in the States, fast MRI, where the AI needs approximately 1/4 of the raw data in order to generate the same quality image and give a response. So you can actually spend 1/4 of the time in the device just getting the number of slices you need. I'm not even talking about ultrasound, where, I mean, it seems obvious. You just stick a pad on, the AI does the work for you. You can send the patient home. There's already work being done on, for example, post-ICU congestive heart failure, patients taking the ultrasound home, sticking it on them, and getting told in remote by the cardiologist, okay, so now you need to come in for additional diuresis. Next thing that I'm going to be mentioning is diagnosis. So you know this, and I just do want to point out something important here. There's a big difference between things that are textbook knowledge and are yes/no questions, and can be put into a simple flow chart that if this test is positive, you go to that. If this test is positive, you go to that. Diagnosis follows this sort of thing, and these tests, which are closed questions, are where the large language models perform the best. The places that the large language models do not perform well are the places where there is a high degree of complexity and where there are temporal issues, like the patient in the past had this, then they had this, then they had this, then they had this. So that's still an issue for many of the models. And the third place that they don't do well is when there is very little data, and you need to extrapolate from one situation to another. So those are the places where things don't go well with these tools. But for passing a multiple choice question, I'm not surprised that they do better than most of us, because the amount of memory, it's like sitting with a book and getting the book to answer the questions. I mean, it's all there. So what's the big deal? And then I just want to introduce you to this, in case you didn't know. Again, this is something that's not freely available, so I feel comfortable discussing it. This is a large language model where the model actually discusses things with the patients. They're checking it currently with primary care physicians, which, by the way, spend an approximate between 2 to 3 minutes nowadays with their patients, unless they're being paid for time, which is a different model. And this is why there's a great deal of interest in generating this, but it will come to the ICU once it developed. And what they did was they took text-based consultations based on OSCEs, and they gave it to specialists to analyze, and they also used actors to see whether who performs better, whether the private care practitioners did, or the primary care practitioners did, or the actual models did. And in fact, you can see here that Amy performed better in terms of providing the appropriate treatment, in terms of explaining the condition to the patient, in terms of showing sort of like a empathy, okay? So you can't be very empathetic when you see a patient every 2 to 3 minutes, or you're running around in the ICU and needing to do a CPR in the corner, and somebody calls you about a patient in another bed. So I think that there's a lot that we can learn from even that literature that is not directly related to intensive care. And here you can see that both the specialist physicians and the patient actors thought that Amy was better in many of the axes checks. So Here's another one for pediatric intensive care. Again, differential diagnosis, and I highlight, note, this is differential diagnosis. This is not treatment in a high complexity environment such as the ICU, and this is not treatment in a situation when there is not enough data and the patient is outside the guidelines. These are all guidelines papers. So, and the differential diagnosis was actually ranked very, very highly, but you can see still the models in this complex situation, which is worse than primary care, the models performed worse. So we're working in a very difficult environment, and therefore use of these tools in the ICU is going to be more probably deferred a little bit. Treatment decision support, again, there's a difference between treatment decisions within guidelines and without guidelines. So here's just really simple exercise generated. Even with these simple exercise generated recommendations, you can see that many times the model will be telling us to seek medical clearance or we don't have enough information. If you've played enough with your online tools, you will see that many times it will send you to the literature, some of which doesn't actually exist in this situation, or tell you, well, I'm not a doctor. So, and here's another one, and here running forward into things that we could, like smaller things that we could use in the ICU. So you can see here already for diabetes, there's been a huge amount of literature showing that you can use AI for diabetes for predictive models, for training the patient or training the doctors, if you wish, for recommending diagnostic and imaging technologies, for prevention, for recommending prevention as they leave the ICU or even at home. And here you can see how quickly the AI will correct the blood glucose when it comes out of as it's rising. So the response that an AI can generate for a single test, for a single pathological parameter is much quicker than what we can do if we know what the parameters it needs to lead to are. So when you're looking at a narrow application, it works very well. When you're looking at broader applications, not as well. Here's another one talking about prognostication and clinical decision in terms of ECMO. And you can see that there has been a lot of literature on this. I'm not even going to go into this because there isn't enough time. This is a whole talk into itself. And here's another one talking about mechanical ventilation, anything from high flow nasal cannula recommendations, when to intubate, when to extubate, some of that you've seen before. So there's a whole broad field that's being developed, and there's so many smaller applications. I can only say that mechanical ventilation is probably going to be easier to develop for things that we know and are clear cut. But decisions such as when to intubate, when to extubate, we know still that we don't know enough. Our information is not sufficient to impute the parameters that will allow these tools to make the decisions. If we're clear about what the parameters for the decision are, like glucose, then the machines will perform well. If we are not clear about the parameters, then there's going to be a problem with imputation. And then here's another one somebody's already selling this, believe it or not, online, saying, I'm going to tell you how to treat your patient here. I will tell you how to do this. And there's a whole bunch of groups that are working on developing this together with those developing the tool. Some people claim that AIs will be able to assist us in also making ethical decisions. I would argue that ethical decisions differ between locations, between people, and therefore you cannot generate a single ethical recommendation for all. You can sometimes determine thresholds, but you cannot make a deterministic ethical decision at this point. And the next thing is the importance of AI cooperative decision making with, and this is a paper that Matthew showed that was his, Dr. Komorowski before, One of the things that I liked about this paper is that people did refer to expert opinion when they were unsure, and you can see this here, when they were unsure of the answer generated. But you need to be unsure that the answer that is generated is not good. So how are you going to get to that level in the first place? And second, you have to have that expert to refer to, which is also a problem. And that may not be in the future once we get told your expert is the AI. Finally, documentation. I'm going to just run through this very quickly. You already have medical record snapshot tools being done. You already have, here's another company saying, abstractive health. Let us summarize your healthcare documents for you. And there have been studies showing that that the LLMs don't do it as well as we would like to. They invent data. They will add on a temperature if they think that this case fits sepsis. They will add the diagnosis of the complaint of chest pain if they think that everything else fits the pattern of chest pain, even if the patient didn't complain of it. So you have to be very careful when you're using these tools. And again, incorrect reasoning. Guys, incorrect reasoning is a mistake. Okay, let's just call it by name. And there's also event inconsistency, meaning we're inventing stuff. These are hallucinations in the charts. And I'd like to end with a word of caution. The market at the moment for, and this is the medical AI market, and you can see AI is a huge thing, is expected to be $208 billion by 2030, which by that time probably I will not be standing on this stage. But this is the market that we're dealing with in terms of potential and what we need to do. And having said that, this is how it looked up to 2021. 2025 is much, much higher. They're talking about a minimal value product and not the product that we want. So I think if we don't want to get to this stage where we are demonstrating, when we're saying, well, this is being forced on us, we have to say, these companies that are getting all this money, we need to be in them. We need to be telling them what we need and not waiting for them to tell us what we need. And with that, I'll thank you.
Thank you, Sharon. That was fantastic. And now I would like Dr. Pinsky, Michael Pinsky from University of Pittsburgh, to join us for his talk.
Thank you very much, Ezra. It's an honor to be here in this group with machine learning and artificial intelligence. Assuming this works. There it goes. What I was asked to talk about is how do you create a realistic system and have it work in your hospital? We have a conceptual problem, and that is that most of the critically ill people are in the ICUs, but we call the codes on the floor. How is that? The reason is we're missing the critical illness on the floors. And the delay in management of those patients can be very high. Okay. So we don't recognize critical illness on the floor or in the step-down units as well as we should. And they're being monitored, but we're just not assessing the monitoring. And clearly the consequences can be catastrophic. We need to assess in step-down units and on the floor how critically ill they are. Now, we recently published a paper that Ezra is an author on as well, in which we summarize the use of artificial intelligence approaches in critical care and its opportunities and obstacles. And the figure from that paper, shown here, gives you the various steps it would take to go from an idea through to the implementation of an intelligent clinical decision support system. And the important point that I wanted to raise from this slide is that there are numerous stakeholders that have to be involved along the way. You do not come up with it yourself, and it is not a single person system, and it is living. Okay. Since I was asked to talk about creating a clinical decision support system, I'm going to show you one that we created and worked. These are the people that did it, and we used the system that was developed by Lionel Tarasenko at Oxford University Medical Center. He's an engineer, and it's Oxford Vital Signs. And what he did was he used an artificial neural net of vital signs of 100 patients with supervised machine learning to identify from simple non-invasive vital signs, blood pressure, heart rate, respiratory rate, and in his case, temperature, whether or not a person was sick or not. Okay, and we created a score from 0 to 10. 10 was bad, 0 was good, and if it went up, it was higher. Nothing more fancy than that. And what he was able to do, and he came to Pittsburgh and we did it together, and as a matter of fact, I met him 20 years ago at this meeting where he came and showed me what he had, and we agreed to do this at the University of Pittsburgh. And what it does is it gives you an alert when your vital sign index goes above a certain level. You still have all the other alerts you have on board, but this one is an integrated one and is very robust. And this is the original paper that he wrote on this in 2006, and we started our study in 2007. 2 years later, we got our first NIH grant to look at machine learning and critical illness, and I've been in this field ever since then, which is about 20 years. Okay. So here's a patient's bedside in a step-down unit, and there's your usual monitor right there. This is the new one. There's no new monitoring that was required. The nurses at the bedside need not put a single thing on that they don't put on automatically. All we did was take that information and put it into this monitor, and the display from the monitor is shown here. The things on the bottom are the things that are measured: respiratory rate, blood pressure, SpO2, and heart rate. The thing that's new is up top. This is the artificial neural net devised pressure, in which we have a pie. The size of the pie gets bigger as the number gets higher. The cuts of the pie tell you what are causing the instability from respiratory rate, heart rate, etc. And on the bottom below, it shows if it's above a dangerous level, it's red. Mickey Mouse. It couldn't be simpler. With this system then, we decided to study it in our patients. So we put the system into a step-down unit in which we had every bed instrumented with it, and they also had the information shown at the nursing station, but we hid it from everyone. And for 8 weeks, we simply collected the data, and we recalibrated the vital sign index to our own personal patients during the next 13 weeks, of which we opened up the screen and said, this is what the screen looks like. And in the last 8 weeks, we said, no more Mr. Nice Guy. If the machine goes beep, you absolutely positively have to see the patient, and if they're sick, fix them. That was the only instruction we gave them, and this was a nursing-run study. Why? Because nurses get it done. Doctors are not reliable. Okay? The phase 1 results, we had 333 patients in the ICU. 40% of the patients we discovered. We did not know that. We're not getting continuous O2 saturation measurements initially, because the nurse had to report the O2 sat every 8 hours, so that he put the pulse oximeter on every 8 hours, got a number, then took it off. So one of the things we discovered was they needed to put it on. We got the O2 sats continuously after that. Most patients in a step-down unit are extremely stable. Instability occurs only in a few patients, and when it can, they get quite ill, and it's often unrecognized. We had a medical emergency team activation threshold that said you need to call a code. Someone has to run to the bedside, and we found that happen in 7 patients, and we were able to identify all of them in advance. And the mean time that our machine said you have a patient that's unstable prior to the time that a code was actually called in those patients was 6 hours. And this is consistent across all studies since then. Patients identify themselves as unstable hours before they die. Hours. It is not a falling off a cliff. It's rolling down a hill and finally drowning in the lake. Okay? Regrettably, 78% of the patients in this blinded part of our study who met the criteria, and we're talking a heart rate of 140 for 1 hour, never had a code called or had any note in the nursing records. I was getting chest pain looking at the records. Cardiorespiratory deterioration is generally not identified, and this was our original paper showing that. This is an example of one patient in which they had MET activation, and as you can see, the VSI is on the top. This is 8 hours. It's not the way you normally look at vital signs. It's a shorter period. But as you can see, the machine was going off many times. That's when we called the code. Furthermore, in all of these times here, every single vital sign was normal. So intermittently looking at data in patients is a very inefficient way of checking out what's going on. So the conclusion of this initial thing was we're missing these patients and that we have to find out what we're doing right. So we then did our study, and we first asked the question, how receptive are our nurses to seeing this information? And this was a study done by Amy Klontz as part of her master's in nursing. What we looked at was how often is SpO2 measured during this phase 1. Remember I told you it was only 40% of the time it was continuous? When the nurses were told that this information is necessary for us to be able to calculate an illness score, because if we have that, we can tell you better what's happening with the patients, we were able to get the O2 sat, continuous monitorment, over the threshold value that we set prehand of 75% almost immediately, and it remains to this day. Then we wanted to say, is it working? Well, this is our medical emergency activation system that we use. If it's there, we call a code. We weren't telling them to do this. We said if the machine goes above 3.2, see the patient. If you can't fix them, call a code. It was as simple as that. And so we actually went from our original value that Lionel Tarasenko said was 3 up to 3.2 because it gave us a better receiver-operator characteristic separation. Our system had to be integrated with the electronic health system. We did it manually. We literally ran wires from every bed into the central system, into the nursing station, okay? Because we did not have our step-down unit linked to the electronic record. And to do that, we brought it all in, brought it back, and this was our decision tree. If the machine goes beep, if you can fix it, fine. If you can't fix it, call a code. That's all we said. What we found was that a lot of times you would have a machine going beep and there'd be nothing wrong. That would be a hit. That's called an artifact. But when they went something wrong and it was real but minor, that was a min. It was there, but who cares? But if it was really serious, it should be a MET full. And we wanted to determine how well this was. And a senior critical care doctor, quite handsome with a beard, was the one who then determined whether it was MET min full or not. This is an example of pulse ox falling off. This is not a MET, but the alarm goes off. But this is just a pulse ox falling off. I wouldn't call a code for that, but I would go to the bedside and fix it. This is an example of a MET min. This is a person going to sleep, 4 in the morning. Heart rate goes down, comes back up. This is an example of a full. This is somebody that's really quite ill. So the summary of our data, we had the same number of patients, the same number of hours in, the same number of patients were stable. The duration, however, of MET minimum markedly decreased because the nurses came to the bed, saw something was wrong, and fixed it. Both the incidence duration of MET full fell, and the percentage of MET fulls markedly decreased because nobody went to a MET full unless they were a MET min first. And so if you went in initially, you fixed them beforehand, and it might be nothing more than putting the mask of oxygen back on them. In phase 1, you can see the total number of MET all, min, and full. When we went into the phase 3, the number of MET mins was less, primarily because with the nurses aware of it, I think that might be the effect. But what we really did is prevent the patients from having serious deterioration. The number of patients, again, when they had the MET full, fell. Interestingly, the time it took to resuscitate the patients, markedly, the number of patients with MET full fell, and the time it took to resuscitate was less. However, when you had a MET full, the time it took to fix a person once they were a MET full was the same. Once you're sick, you're sick. The trick was we didn't get them there. To summarize these things, using this vital sign fused index, we were able to get nursing buy-in, and we found that it worked. The second part, which is the basis of our subsequent NIH grant, was we discovered that our vital sign index went beep an average of 9.5 minutes before any single vital sign value was in the abnormal range, because it looked at the pattern, and the pattern they saw was abnormal. We didn't tell it to do it, that's just what the machine did. And that's the basis of predictive analytics. And we were able to identify the patients and treat them an hour and a half before any patient got sick. So when they had a code called, there were already doctors at the bedside beforehand. Okay. There's the law of unintended consequences. We did not tell the nurses to do anything, but they started to say, if this works, we're going to go in and see the patient beforehand when the value is going from 1 to 2 to 3, and we're going to fix them so it never goes beep in the first part. Furthermore, we're going to take the more experienced nurses and give them patients which have a higher VSI, and the less experienced nurses can take more patients but with lower VSIs. We didn't tell them to do that. They did that on their own because they wanted to practice good patient care. Nurses loved it. And when we finished the study, we said, okay, we're going to take the alarm off. And they said, over our dead bodies. The reality is that if we looked at the satisfaction that the nurses had over the phase 3, initially they were questioning the accuracy of it, but then they accepted it blindly as being correct because they saw in their own eyes that it worked. Okay? And this was less error with it, and there was less response. So in all metrics, we were doing well. 2 years later, it's still in use. The nurses like it, and now somehow the doctors know it's present, and they look at that value too when they're rounding to take care of the patients, which we didn't tell them to do either. And it works. Unfortunately, the company went bankrupt 2 years later, and so even though the signals were present, it's no longer there. We're using different things now. But the characteristic and the conclusions are that you need to have buy-in from the primary stakeholders treating the patients, and they have to have a trustworthy system that they see with their own eyes, and they will be the heroes that support it going forward. So what we did was we did a nursing training, and the nurses then were the ones that said, we want to keep this, because they saw it improve patient care. No nurse goes into the hospital and says, today I'm going to practice bad nursing. All we were doing is helping them do what they wanted to do, because it alerted the nurses ahead of time. It reduced patient instability. And by the way, they said, you know, once we used your system, there were no alarms going off in the ward. We had more time to treat our patients because all these instabilities were gone. And with that, I thank you for your attention.
Thanks, Dr. Pinsky. We'll take questions at the end of the next session, next speaker, I'm sorry. And so I get to invite back up Paul Elbers, again from Amsterdam. And this time he'll be speaking to us on your ICU can become a clinical AI validation center.
Yes, thank you again, and also thanks to the audience, and also thanks to Professor Pinsky for basically introducing the subject. And I must say I'm impressed that you already taught it as it was in 2008, right? So many years ago. So moving back to current times. So you've already seen my disclosures from Amsterdam, but it's always a good idea to pitch the Amsterdam UMC database, so as you know by now, freely downloadable for all, and both commercial and academic conflicts of interest. So first let me reassure you, so I do not think that you will lose your job to AI, even though I alluded to that a little bit in my first talk. at least not yet, but I think you will lose your job to someone who knows how to use AI, right? So you better start gearing up for this. Importantly, I see artificial intelligence as a companion, right? So not as something that is going to do your task, but try and make your task better. So it's probably better to talk about augmented intelligence. So as Professor Einav already alluded to, there have been estimates of the market value. So going to be over $200 billion by 2030, and that's a lot of money, right? And I think we, as doctors, as intensivists, we need to partner up with commercial companies to make sure that money is invested in the right way and not in the wrong way. So we've seen lots of examples, right, on artificial intelligence, and you are all up to speed with the fact there are three main lines of machine learning. But you have to realize, and you probably know that the ICU is by far the most natural habitat for artificial intelligence. So because for a long time we are registering and collecting lots of data, we deal with high mortality every time. There's a lot of uncertainty on diagnosis and prognosis. So the decisions we make, and we make many of these decisions, come with dire consequences. So how can AI help us? Well, we've seen a lot of examples already in patient triage, diagnosis and treatment, ventilator optimization, hemodynamic management, hemodynamic monitoring, data interpretation, even telemedicine consultation, clinical documentation, resource allocation, the list goes on and on. So if you want to read more about that, we've recently published a number of papers reviewing the field. So this is one of them. Professor Pinsky already pointed out this pretty important paper on opportunities and obstacles, and lastly about large language models, which I've talked to you about in the previous session. So here's the thing. So this is a paper that was published even earlier than Professor Pinsky's paper. So, and the idea here and the main message of that paper was that computing science will probably exert its major effects by augmenting, but also replacing intellectual functions of the physician. And when was this article written, do you think? So look in the right upper corner. So 1970. Yeah, so that was pretty visionary, but it also illustrates a major problem. Because as we have written in intensive care medicine, and it was later followed up by others, that we cannot yet say that intensive care medicine is ready for takeoff. Because at that time, but that has remained so since, 93% of publications are only talking about developing and testing models, but they do not make their way in the clinic. So I've changed my mind about this in recent years because it's also a normal progression, right? So you need a lot of trials for some good examples to go to the bedside. And we are actually seeing implementations of AI now. But I think it could be much more with the help of all of us. And we need to be aware and break the barrier. So the first barrier is the lack of data availability. Second is the lack of implementation, and that is directly related to legislation, especially in Europe, and security, and also a lack of understanding. So doctors, of course, are no data scientists, but definitely the other way around is also very true. So, and this was eloquently put by Obama, and he said, I know a lot of doctors who became recreational pilots, but he didn't know one pilot who became a recreational doctor. So we should be aware of our value as doctors. And I think it is time that we put healthcare professionals back in the driving seat of all these AI operations. So I would like to take you along the vision of transforming your ICU into a clinical AI validation center. And I think that would require a structured approach, but you can start doing this today. And that means that you should balance technological innovation with clinical integration ethical oversight, and regulatory compliance. And these are all fancy words, but they can be practically implemented tomorrow. So it first starts, of course, with data sharing. So I've already talked enough about Amsterdam CDB, but there are also initiatives in the Netherlands nationally, but I'm sure there are initiatives in many other countries to try and combine data of many intensive cares. And in Europe, there's now the so-called Indicate project, uniting data from 25 intensive care units throughout Europe. And the beauty of this, these data are not centralized, but they are siloed so that they are available for federated learning. So the data is not moving to the data scientist, but rather the algorithm is traveling to the hospital and being trained. But this requires that you start thinking today about how you are going to map your data, so the data that is currently in your electronic health record, to common data standards. So this is a picture of the OMOP, Common Data Model, and you should also make sure that if you have the data into a data model, that you make it interoperable, so you provide application program interfaces for that data, for example, using the 807 FHIR standard. So I have been lucky enough to be able to run a number of projects to bring data science and artificial intelligence to the bedside. And I can tell you, I hope this gets better, but all of these projects cost many years of your life, right? And that is because it needs to be safe, but also because there are a lot of hurdles. And you need to walk the roads again and again for every single application. So it begins with problem definition all the way to external validation, but then the fun begins, but also the regulation comes into play, right? So you can do software prototyping, end-user testing, and ultimately clinical testing and clinical validation. But that in Europe requires usually either an investigational medicinal device dossier and under the current regulation of the medical device regulation, which is European law. It also requires a quality system or a CE mark, and that is basically the same challenge because it requires thousands of pages of documentation, which is a good thing, right? But it also is a lot of trouble. So you need to be aware of the laws and obstacles governing this. So if we start with the electronic health record, there's the problem of extraction, and then we go from the data to the model, modeling, and then you finally need to integrate, and you have laws and obstacles governing all of these processes. So for extracting in Europe, you would need to either dive into the GDPR yourself or have a structure and have someone do that for you. For the modeling, you need to take into account the Medical Device Regulation and the AI Act. And for integration, and that is a huge problem in major hospitals because you need to talk to your ICT persons, and they mainly have the task of keeping your hospital running in the first place. So they need to have some persuasion to bring models to the bedside. So some examples I've been able to bring to the bedside over the years. So it started very simple, right, with the asset-based.org steward approach analysis, which can be coupled to the electronic health record. We did a lot of work trying to model antibiotic dosing, and it culminated into a trial in which we provided recommendation on antibiotic dosing specified for a specific patient right at the bedside. So no pharmacist involved. People could immediately see the dose in the graph. But here you see the technical schemes and also the prototyping, and it just requires a lot of either knowledge of multiple fields, or you need to make a team of different expertise, and because you cannot do this alone, right? So it's just a complicated server landscape, software architecture, user interfaces, and this is what it looked like, right? So it doesn't even look that fancy, but this is what a team can do, and people loved it, right? So this is actually a problem because all doctors were very happy to take the recommendation, even if they were sometimes a bit scary. And the final thing we did was together with a scale-up company called PacMed to bring a model to the bedside that predicted whether a patient would be readmitted if this patient were discharged. So it was actually a boost model, so you've seen this many times before, and in clinical practice it looked like this. You would get a score basically indicating what the percentage was when a patient would be eligible for discharge, and the percentage would indicate whether or not he or she would return within 7 days, together with explainability and the evolving of the chance over time. So again, I would like to remind you that I've presented these projects now in 2 minutes, right? But they all took many, many years. And I think we can do better by working together and make this more scalable. So again, following this road, and I've shown you this before, we need to start gearing up for this. And I think what that requires in your ICU is a clinical AI department. So if you do not have such a department now, I think I would suggest you start creating one tomorrow, because it will require quality management system, as I told you, to make sure that the AI gap will be tightened, and that involves people, but also processes, and to ultimately come to a validated technology. So it requires risk monitoring, risk identification, risk enumeration, and also risk mitigation. And that, to me, as a tech-savvy and AI enthusiast, always sounds very boring, but it is a requisite. So we need to do this together. So I have created an 8-step guide for you guys to become an AI clinical validation center. So first, of course, you need to define your scope, because not every hospital can do the same thing. And then first start building your multidisciplinary team. Then you need to develop robust data pipelines. So think about evolving people to transform your current data landscape into interoperable common data standards. You need to establish this validation network, ideally together with scale-up companies or even big companies. You need to have your team for regulatory and ethical compliance, the infrastructure and the funding. And I think it's imperative to collaborate with industry. I think we cannot do this alone as hospitals, maybe with the support of academia. And finally, I think it's on the community to also measure and publish the impact it has on patients. So, finally, what about the costs? Because I hear a lot of people talking, so I don't want this company to buy my data, or I don't want companies to use my data for free and then develop a model that I need to then buy back, right? And, well, I mean, there's probably some truth in that, right? And might certainly feel that way, but ultimately, and I might be a bit socialistic about this, but I think our ultimate goal is to improve patient care, right, as intensivists. And I definitely think it's impossible, because I'm certainly not going to be able to bring many models to the bedside anymore, because it just takes too much time. So we need to do it together, and we also need not to be that worried about giving out data as long as it is within the legal boundaries. Because if you don't do that, someone else will do it, right? And it's much better to open this up and share both the risk but also the revenue. So I strongly believe in shared revenue models, and I definitely believe in only paying for clinical impact. So we as a community should demand that we only pay if these models improve outcomes. So that means balancing intellectual property with open science, and for me that means data solidarity. So it's a concept that we don't see the data. I mean, of course it's valuable, but we don't need to be selfish about it. So start sharing and start preparing your ICU tomorrow, because I think that your ICU really can become a clinical AI validation center. And with that, I thank you.
So I will again invite our last three speakers up to take questions from the audience. We're a tad over time, so we don't have as much time for questions this time. And so while I certainly have burning questions, I imagine Azra does as well. I want to give some opportunity to see if there are any hands in the audience first. It's very hard to see from here. You're running to, okay, you're welcome, someone, excellent.
Hello, good morning. I would like to ask Dr. Paul regarding establishing the clinical AI department. Is it required to be a physician or a computer science or combine of these two? Can you explain in this issue?
Yeah, so I hope to convey the message that we need people from many disciplines in that team, right? So of course physicians, but also nurses, but also data scientists, but also legal people, technical people, probably ethics people. So, and some of these functions can be combined if your hospital is smaller. But I think, I mean, if you see it, it's what is coming and the way this technology is being pushed, I think the bigger the better.
I was going to make a comment that in all of these processes, you need to have the data, and the data has to be good. And so whether you like it or not, you have to deal with the hospital information systems. And the hospital is not your friend. The administrators want to block you at every time because of all of the risks that they are adverse to being with. And it took us years to be able to finally get a pipeline of data from our own medical center. And we've been doing it for 20 years at the University of Pittsburgh. It took us years before they'd allow us to get minimum amount, and they wouldn't give it for free. We had to pay for it. And if we didn't have grants, we wouldn't have done the research. But then you ask the question, who's creating the models? The computer scientists, some of which have become MDs as well, which is wonderful, but most of them aren't. They don't know the difference between a softball and a heart in terms of data. It's data. And if they see an association, it might be highly statistical, but have nothing to do with patient care. So they are brilliant at what they do. But we don't know how to do their tools very often. So we have to sit literally elbow to elbow with them as we're going over the models so that they can show us what they can get from these supervised, unsupervised, game playing, all the different, we use all the models, we use all the techniques to find out what's best clinically. And then, so it has to be a partnership. If you want to make it really screwed up, you say, I'm the doctor, I want you to show me that you can do this, and they can, and it won't be valid, but they'll show you it'll work. Or they can show you how to do something, and it can't be measured and is clinically unrelevant. So you have to have a partnership between the clinicians who know what they want and have their own expert domain in physiology and patient care, and the computer scientists that understand how to manipulate big data sets and do the modeling that they need to do.
Michael Hessian from Sydney. Could you just, Professor Elbers, comment on the data set that we need to input? I think you're saying that we need a standardized data set, which we've always imagined, but Professor Schenck this morning, I thought, was saying, when he gave that example about the problem-based medical record, that we're better off interpreting free text with AI to provide our data set rather than to use the standardized database. Would you comment on that?
Yeah, but I think Sharon might actually be better at that.
So I can say, first of all, you need to decide on what your question is. If you're going to take something very specific, then you need all the relevant data for that question. Because you can import tons of data, which is currently what's happening in the EMR, but won't know how to use it if you're not asking a focused question. So first, it's almost like any research. If you don't first define your research question properly, you're not going to be getting a reasonable answer at the end. I think that's the main thing.
Yeah, and if I may add to that in terms of data structure, so you're probably right that AI in the future and large language models will probably be able to dive into natural text and get out the data anyone would want in a structured fashion. But I think it's also very important to start educating your SEO team in thinking along these data structures. So, and then that either requires adhering to common data standards right from the start, so registering it as such in the electronic health record. But if that's not possible, and it usually is, then at least try to find a way to transform that into a common data model. And of course, you can use large language models to help you with that. So my idea was not so much to highlight the technical challenges of that, but more to introduce this as a concept that you need to bring home to your SEO.
In the United States, I think Leo Celi is in the audience here and is going to talk, and Gilles Clermont from our department are running a National Science Foundation, NIH-sponsored harmonization of data structures across all medical centers with the goal, at least in North America, of having a data structure so that you can apply models across systems to look at it. What information you put in it is a function of what you collect yourself. But if you have an MRI, it'll be in this point in the data structure, and it'll have a format of data reporting that'll allow you to pull it into your model. So the answer is, what information you need? All the information I can get. The machines will throw out the information that it doesn't need because it's not useful on what they're looking at. But you have no idea, if you don't know the question, what the information is. So one of the fundamental things that we are doing and have to do is we have to create a common data structure framework that you then populate with the data from your systems. And this is being created now, but it doesn't exist as an operational thing at this moment, but it hopefully will be very soon. And hopefully Dr. Celi will be talking about that a bit when he gives his presentation later, which I will miss because I have to give a talk in another room almost immediately.
Thank you. Thank you so much for our panelists and speakers. And thank you for introduction, pre-intro, for Dr. Leo Celi from Boston. He's a principal research scientist and clinical research director of the MIT Computational Lab. Leo is going to talk about, are the models ready for prime time?
Thanks for the introduction. Every year I complain that people don't come to the AI sessions, and I'm hoping that over the next few years we could change that, because AI is no longer an option, it's no longer an elective, it's no longer a research topic. We are breathing AI now, and it's really up to us whether we would like to be swept by this tsunami or whether we take control of this movement. There are no significant disclosures that are pertinent to this presentation, but our group has received research funding from the National Institute of Health, National Science Foundation, as well as the Ministry of Health and Welfare from South Korea. I'm going to start off with 5 reasons why we need to be careful with the use of generative AI, specifically language models. The first is the phrase sycophancy bias. If you haven't heard that, please memorize it. And this is the attribute whereby language models, specifically the creators of language models, want us to be addicted to the use of language models. So they're going to try to please us. They're not going to suggest any perspectives or opinions that are really discordant with our mechanistic models of disease, which means that this is an opportunity to reinforce existing biases. And it sounds like social media, right? So AI is really social media on steroids, except that with social media, you're aware that the people who are commenting on your posts are peers. With AI, you think that these are oracles who have access to all the knowledge encrypted in the digital world. And for that reason, you take their suggestions as ground truth. So sycophancy bias, and then their perception as experts. Number 3, of course, is that generative AI is still trained on human data, which means that it will learn all the biases that we have as humans. And then there's the black box reason that we've heard over and over again. And I would tell you that I am in the camp that thinks that explainability is a myth. It's a delusion. If you think that you could really figure out with SHAP values how a model arrived at an output, you are fooling yourself, because this has undergone layers and layers of representation and attention, that to think that we will be able to figure out what led to this prediction or classification is just an illusion. And finally, this pertains not to AI itself, but to society. We have this techno-optimism. We have this pious hope that we can fix broken systems with technology, with innovations. And hear this, any system that cannot be fixed without AI cannot be fixed with AI. Any system that cannot be fixed without technology cannot be fixed with technology. I'm going to go through some papers that were published for the most part last year that will question, challenge the hype of AI, that it will improve our accuracy, it will improve our efficiency. This one was published in September of last year, and what they did was to randomize emergency and neuro radiologists with a tool that will help them read very quickly CT scans taken from patients who presented with stroke. So it's very straightforward. Is there bleeding in the CT scan or not? And what they did was to measure the accuracy of the group of radiologists with AI, as well as the group of radiologists who were given this tool. And then for cases where there seems to be discordance between what AI read and what the radiologist read, they put together a consensus of radiologists to determine which final diagnosis is correct. And what they found in this prospective trial is that there is no improvement in the accuracy. There is no difference in the radiologists who had AI against the radiologists without AI. There was also no reduction in time, in the turnaround time of positive scans. They were not able to give that information sooner to the emergency room doctors who are taking care of the patient. This next study was published months before, actually, from Pranav's group, and they also did a prospective evaluation of radiology AI. And the hypothesis was that it will improve the performance of the more novice radiologists who are just fresh from their fellowship training. And for those who are seasoned radiologists, it probably won't have that much impact. And of course, spoiler alert, they did not find that. What they found is that there is a heterogeneity of treatment effect. So the thinking that we will behave uniformly with respect to having an AI co-pilot, again, is wrong. What was most concerning about this study is the finding that some seasoned radiologists started making more mistakes. And when they interviewed this radiologist, they were saying that as soon as AI gave them a different reading, and it turned out that AI was correct and they were wrong, they started losing confidence and they started making more mistakes. This next study is a proof that humans in the loop is not gonna cut it. We always think that, oh, as long as you put clinicians there, then we will all be good. We are on our way to incorporating AI and improving healthcare delivery. Wrong. And this is a prospective study once again, and they compared humans alone versus humans plus AI versus AI. And in a good significant fraction of the cases, AI beat humans plus AI. So we need to think twice, again, about the design of human AI systems. This is a paper that was published a year ago, really saying that clinical vigilance cannot be trusted in terms of being able to tell whether humans are able to evaluate the output of AI. And of course, what makes this even worse is that we're not training clinicians on how to evaluate AI. This is still not part of the core competency of clinicians, of intensivists, of doctors, of clinicians. So we need to rethink our strategy. This is an interesting study that was performed in 2015, where they had incognito Department of Homeland Security personnel who tried to sneak in weapons through dozens of the busiest airports in the United States. And the TSA failed in 67 out of the 70 tests. In one case, the alarm went off and the incognito Homeland Security person was patted, but they did not notice that there was a plastic explosive that was actually taped to the back. So to me, this is a good story because airport security people are trained to look for water bottles, and they're very good at detecting water bottles. They do not get training, and the only weapons that they really discover are the ones that people forget. The hand grenade that they accidentally put it in their day packs. So they don't do a lot of training of instances that are difficult to detect. And I think that this is also going to happen when we include AI as part of our intensive care units. There is this concept that is quite known in the cognitive science world, and it's called inattention blindness, automation blindness, automation inattention. Humans are very poor in keeping vigilant, especially in detecting instances, as I said, that might look invisible. And this is why we really think that we need to overhaul medical education and clinical training. We need to equip our doctors and nurses and pharmacists with a new agency to be able to leverage this very powerful technology. Automation blindness cannot be automated away. Study after study has shown that we become less vigilant over time, especially as we trust a technology that we have adopted. I just wanted to remind people of the fact that we have been successful in some systems, not because we created better products. So two very good examples for that is the aviation industry, and the other one is road safety. It's not just about building safer planes and safer cars. We need to have a very comprehensive regulatory oversight of the entire system, and we need to have public advocacy as well so that we achieve the aspirations that we have in terms of improving healthcare with a technology such as artificial intelligence. I keep saying this. We need to stop building AI models. Instead, we need to start designing human AI systems. We need to design human AI systems that are resilient to human frailties, human weaknesses, human vulnerabilities. We need human AI systems with humility and curiosity at the core. A human AI system that is driven by curiosity rather than the traditional external rewards such as accuracy might help agents learn better in challenging environments such as the intensive care unit. instilling curiosity in AI systems is critical, as it may enhance our ability to learn and adapt in complex and sparse reward environments. More importantly, we need to embed humility and empathy in human AI systems. We need to embrace that at any point we can be, and indeed we are biased to some degree, because this should motivate us to constantly seek challenges to our way of thinking and our mechanistic models of diseases. So how do we imbibe epistemic humility and pursuit of plurality in scientific thinking? We are seeing AI everywhere, and my definition of AI is arrogance and ignorance, not augmented intelligence. Epistemic humility, so this understanding that at any point, the way that we view the world could be wrong because that is a product of our experiences, our exposure to information and knowledge. Epistemic humility creates a forcing function that brings people who think differently together. Humility and plurality, and they go hand in hand, will keep us grounded. On this note, we actually organized a symposium on epistemic humility at MIT in January of this year. The event sought to address human design flaws and societal techno-optimism that may impair our ability to innovate and evaluate technologies. AI requires that our systems for learning are designed and operated by communities. Finally, in reinforcement learning, the successful adaptation to changing conditions requires a certain level of diversity among agents' actions. In the work of Nobel laureate Daron Acemoglu, they found that the most effective social networks combine strongly connected agents with smaller communities that maintain diverse choices through weak links. And finally, you've seen this phrase over and over again: a system is perfectly designed to get the results that it gets. The way we deliver care is informed by a knowledge system that is perfectly designed to produce health disparities because our knowledge system is quite biased. The way that we are building AI models right now is perfectly designed to perpetuate stereotypes and structural inequities. But what exactly are we referring to when we say system? A system is not just the organizational structure, a compendium of policies, or even the data infrastructure. A system is the unwritten set of rules that dictate how we think, how we learn, how we solve problems, and most importantly, how we work together. Thank you.
Thank you, Dr. Celi. And then our second speaker for this section, I will invite up now, that's Vitaly Herasevich. I apologize if I mispronounced your last name. And he'll be speaking to us on how to evaluate health information technologies and AI algorithms.
All right. Hello, everyone. And yeah, in the next 15 minutes or so, I'm going to talk about importance of health information technology evaluation. I have no disclosure rather than publish 2 textbooks on the topic. We talk a little bit about terminology, and we will talk about methods, how to use that. Why we need to do health information technology evaluation? This is a random website, and when you log into this website, you immediately can see some advertisement. They say, for example, this website says they reduce a lot, make a lot good stuff, but really we don't know how they test all of that. What was setting when they did this? What is the sample size? What is the comparison group, if any? How biases was addressed, and how statistical analysis was done. We really don't know. Is it just marketing material? Is it just very smart marketing, or this is reality? And like anything in a clinical epidemiology, there are a real causal effect and number of the biases on top of that. And these biases, they really not described in that, not addressed or anything like that. Okay, that's something from Chief Information Officer of Johns Hopkins, and he said what clinicians often given tools which designed by engineers, and engineers really don't know what clinicians think what is important. And the problem is because they use very different languages and apply different theories for these systems when they develop them. Really, in industry, when industry do something and they mean standards, it's a technology which is manufactured to the standards. If they say this is brick and they develop brick which performs well, that's a standard. In clinical world, standards determine what equipment does something important. If you say this is blood pressure monitors, that means it's blood pressure monitors and measure blood pressure. This is interesting except from user agreement. We probably, like any software, like in a Windows, you just click accept and so on, never read this. But this is EMR user agreement. The long story short, they actually take no responsibility for anything what this software can cause to patients, to physicians, to anybody, and they cannot be sued for that. You take responsibility when you use these systems, EMR or AI or any tools like that. Okay. Why we need to do evaluation? First, we need to make sure what technology is safe. Then we need to understand what technology does something what is important and useful, and can this apply to our practice. In United States, everybody think immediately about FDA. Why not FDA? And FDA is a body which do regulation, but they usually look for a number of the technologies plus food plus some cosmetics product or so, and include medical devices. But simply they require two big kind of the items. Is this technology safe? Does not do any harm? And performs the function claimed. Again, just like use analogy of blood pressure monitors. If you say this is blood pressure monitors, it's supposed to measure blood pressure, nothing else. That's in a like very high level FDA regulation and so on. When we look to software, medical software, that could be divided to two big groups. One is not regulated and another regulated. Non-regulated is administrative software, which probably nothing to do with patients themselves, like scheduling, billing, or so. And there are clinical decision support system, electronic medical records, alerts, decision support system, they're not regulated. They're not supposed to be regulated. And there are medical software devices which are regulated, and they usually divide to three classes based on the risk, class 1, 2, and 3. And there are still no requirements, no regulation how this artificial intelligence elements could be evaluated and regulated. That's a paper from 2021. Authors try to organize and see what is AI as a medical device was approved by FDA. And we can see a lot, there are squares and circles, they means, yeah, is it like multi-site, single site, and the risk of them. But we can see what there are not really much technology went through the FDA process as a software, as a medical device. Okay, what is important to evaluate? Let's think about health information technology stakeholders. And again, this could be beautiful AI algorithm or any kind of the decision support system. There are a number of the stakeholders, and probably biggest stakeholder group, patients and families. And they really need to know like answers to two questions. Is it safe? Is it help me? There are another group of the stakeholders, clinicians, and clinicians, they really want to be sure what this technology, again, is safe, and is the technology kind of user-friendly and do something useful. There are another group of the stakeholders, which I would say developers, vendors, or on the hospital side, IT and security. They really worry about support, how much effort they would put in this support of the technology, what is security of this, how much troubles they would have with technology. And there are administrators or purchasers or decision makers who make a decision to buy this technology, and they mostly worry about return on investment. As we can see, we have one technology, but there are a lot questions around it, a lot of stakeholders, and there are no single answer for that. We really in a technology evaluation, can group all these questions what we need to answer in 3 big groups: better health, better care, and lower cost. Everything could be divided to these 3 groups. And answering this question, we can address these 4 stakeholders groups questions. Okay, what would be main criteria for this evaluation? It's a technology capability, range of possible use, diagnostic accuracy, impact on the healthcare providers, and therapeutic impact. There are another one, patient outcome. Obviously have this group of the questions to answer could address all these 4 big stakeholders groups. Nothing new here. This is typical structure of the clinical study. We prepare, we do protocols, we get approvals, we apply appropriate methodology, carry out study, and publish a report. It could be scientific report or anything back to stakeholders. In terms of the frameworks, first we do safety evaluation, then we do efficacy. This is something when we measure technology without applying to patient care. It's a kind of dry run or safe environment or something like that. Effectiveness, it's a measured technology applied to the patient in a real world scenario. And also we measure cost, because at the end of the day, this is for a group of the stakeholders, administrators. They are interested in cost saving or cost adding. In a study design, there are really 2 big groups, and I will not stop on any of these elements, but one could be active. This is laboratory-based. Laboratory we can have in quotation. And passive, which actually observational study or interventional study on the clinical side. A lot could be done to understand how this technology works on the laboratory-based side, which is performance diagnostic studies, surveys of the providers, and all kind of the studies which we not execute on the patients and not do anything to them. But another part is a study which in real life. Again, to repeat, efficacy, it's something what done in an ideal condition when we have done this without impact of the patient. And effectiveness, it's average conditions. That means we apply as it is for a real life environment. There are more kind of equivalent of the pragmatic trials or so. And from ultimate outcome measurement, we really want to reduce mortality, especially in ICU, but it's really difficult to do with any technology. There would be no direct impact on this metric. But probably what we can do is improve symptom control. And one another metric especially important these days, improved patient family satisfaction. There's a three big group of the outcome measurement. I finish my talk with some case. This is was done many years ago. We did score. I mean, these days everybody does some score. We did score, it's called Swift score, and this score calculates risk of the unplanned readmission to ICU after discharge. And from mathematical standpoint, algorithmic standpoint, that was excellent score, excellent accuracy, could be predict reliably ICU readmission. And from academic standpoint, it's a success. Paper, everything done, and usually finish this article with some quote. That's ready to apply to the practice. Then we did automatic tool. People call this dashboards, but that was electronic tool which automatically calculate the score on every patient in our ICU. No human impact, beautiful tool, beautiful usability, everything on the screen. Again, excellent paper. You can publish this, you can say we developed great tool, everybody like it, automatically calculated, no nurses involved, perfect. And then we give this tool to clinicians to use on the discharge planning. And we found that there are no impact on the readmission. Excellent score, excellent tool. They use this in a lot of cases, they turn decision about discharge. And this still not affect unplanned readmission to ICU. Okay, that's something what I would like to highlight. Health information technology evaluation, Paul told before, this is team sport, and people from different expertise, with different expertise and different skills need to be involved in this. We need to work with people who understand all these fine-tuned pieces. This is my last slide, and as I mentioned, we published 2 books on the health information technology evaluation. That's in United States under HIMSS, and always open to questions. There are my email address below. Thank you.
Thank you. We have exactly 14 minutes for questions. So I would like to invite our speakers at the podium and would like to open question session. We have microphone. We have one person here. First row.
Thank you for your nice presentation. I am Fadel Muteri from Saudi Arabia Government Hospital. Actually, every time I attend AI symposium or lecture, I get more excited, and after that, there is a question at the end came to my mind. First, is the outcome of use of AI improve our healthcare system, improve our healthcare care? Second, I met one of the industry guy, and he told me this AI in medical, it will be ended by medical black box, like a black box in the airplane, and all this data, it will be available. But the problem, the ethical issue in this data, how can we organizing it? Thank you.
Yeah, that's to repeat question. The first question is AI can improve patient care, and second, a question about black box, like algorithms in black box. Yeah, that's And in terms of the technology, AI is a technology, and any technology miles could be vary. Some technology have bigger impact, some technology they have smaller impact, some technology have absolutely no impact. AI no different from other technology. When we have something like manufactured, we really need, again, it's back to evaluation, we really need to understand every technology. There are no simple answer for that. And for a black box, we're still in a time when black box consider something awful, or we think we need to understand how AI works or this technology works. And I use this example quite often. Blood pressure monitor. Many years ago, we had manual device which you pump, cuff, and look to manometer and see and understand how it works. Now, these days, it's just one push button and some black box and electronic inside, and we are not questioning this, what is the voltage inside this box device. We just trust this measurement. Exactly the same with AI. I mean, we are in transition period when we get to the point when we say, okay, that's a technology, and we accept this measurement or output because we trust this technology.
Do I think it will improve healthcare? Yes. I won't stay in this field if I don't think that we will be able to really leverage this technology. But it requires a very different approach. It requires a very different set of skills. It requires a new agency to be able to navigate the future. I don't think we could even imagine what the future looks like. The people who made the internet in the late 1980s, they have no idea what it was going to produce. And in that sense, I really think that we also don't know what the impact is of AI. Like, who would have thought that we would be this good at critical thinking as a result of AI with apps like WhatsApp and Zoom? Like, the way we think now is very different from the way we were thinking 5 years ago. So am I concerned that we will be lazy and less critical thinkers with AI? Yes, I am concerned, but it will also perhaps free us to think more creatively in terms of how we create and validate knowledge, and how we are going to create and validate knowledge with AI as our tool is going to look very different with the way we created and validated knowledge. So there's a lot of room for improvement. I think that it's obvious that we're going to improve because our baseline model is so bad. We are harming patients every day. So I keep saying that it's quite hypocritical of us to make our medical students say, first do no harm on the first day of medical school, when in fact we know every day that we are harming people because our understanding of health and disease is not full. So this is what excites me. I think this is the legacy of AI. It's going to make us better critical thinkers, be able to be systems engineers. So we have been debating about what would the doctors be like in the future when AI can diagnose better and AI can produce treatment recommendations better than doctors. And then when we have advanced practice providers who can do procedures for us. So we have to change our professional identity. It's not anymore the great thinker or the knowledge expert or the proceduralist. It's going to be a systems designer, systems engineer, as Asra would say, strategist, as I would say, an advocate and activist for our patients. So our aspiration to be leaders are going to switch over to our aspirations to be role models. So we need to rethink exactly what would be our role, because I think that role is going to be completely different from how we are doing it now. And we need everyone's help. We need more people to think through these issues because they are actually very challenging. They're almost very daunting to a point that we're paralyzed by our inability to reimagine. I keep saying that if we fail this, it's because of a failure to reimagine what the world could look like. And to be able to do that, we need to bring in non-traditional actors. And I'm so excited that we have lured computer scientists and engineers to think with us, what would be the design of healthcare delivery systems of the future? We've never asked them before because we were too AI, we were too arrogant and ignorant to think that they will have some contribution on how to deliver care. So I think that's a challenge for all of us. And I want more conferences to talk about these issues. And I keep saying that, oh, everyone is still flocking to the talks about sepsis and ARDS when we need people to start thinking very differently. And probably, perhaps, we won't learn it from those talks. No offense, like I also go to those talks, and I also give those talks. But we need to incorporate more out-of-the-box discussions to be able to prepare us, to have that, to develop that agency to navigate this post-AI world.
Hello. Hi. Good morning. Dr. Makalintal from Philippines. I just want to express my deep appreciation for the symposium for coming up with talks like this because this is what we really need. As a backgrounder, I'm involved with the database integration of 45 national insurance companies back home, and I really appreciate the talks that are being done now. Hopefully, sir, we can have more talks like this that will help us guide our hospitals, guide our colleagues on how we will deal with this technological tsunami that's coming. Hopefully we can have this more often and we can include this in our yearly conventions instead of, aside from the emergency and intensive care. Thank you.
Thank you.
Yes, and I just wanted to advertise that we're always happy to help co-organize courses, similar to the one that we have here. So we travel every month to different parts of the world. A good fraction of our trips are in low and middle income countries. We think that the way to do this is to truly invest in capacity building, not try to sell these poor countries AI tools that were developed in rich countries, because we know that that is going to make problems worse. So the focus really is not anymore what do we build, but who should be building this and how should we be building this. And I wanted to introduce the phrase community science to replace open science. Because what we found is that the open science concept is leveraged disproportionately by people who have privilege and who have access. So somehow we need to make sure that we bridge communities that can take advantage of the open science movement, in which case it has to be a focus on the community rather than the data itself or the software itself.
Sure, I'll take the moderator opportunity to ask a question. I don't see any out there. I was really intrigued by the combination of your talks, the idea that we needed to have humility, that we need to think about sort of what the purpose of our AI is. And then I really liked the comment that you made, Dr. Herasevich, about the fact that we don't necessarily regulate devices the way that we regulate medications, for instance. And I'm curious if you think sort of the horse is out of the barn. Have we already created a circumstance or a situation where we don't have the regulations in place to allow us to have these systems be humble and be sort of aligned with our values? And if so, how do we deal with that?
Yeah, that's a great question. And I mean, regulation is a great, when you what is the current landscape in United States? Yeah, regulation is required when you sell it. Yeah, when you sell this technology to a third party, they regulate it. And again, that's a lot from the history when something what I mean, in a sales world, they have something what not perform to the function. But the good part of that, if you develop this technology to your own practice, you don't need any regulation because this is your own responsibility. No matter what tool you use for a patient care, you have final responsibility. And that's a kind of like gray area currently. A lot push to get this regulation applied to every single piece of that. And if we're talking about algorithms, they constantly improved because there are reinforced learning, there are changing a practice, something what we have done on the sepsis 15 years ago. It's barely applied these days because practice changed over the 15 years. And that's already unknown, and it's a gray zone. Is it every single tweak of algorithm need to go through the reapproval again, or you just get basic approval? There are no answer on that.
So similar to AI, similar to technology, we think that the regulatory frameworks should be hyper-local. They should be agile. They should be more inclusive in who gets to decide what should be the regulation. They should be reflective, which means you're constantly monitoring what is the impact of the regulatory framework. And they should be reflexive. You should address the challenges that you see. Unfortunately, all our legacy systems for education, innovation, and regulation are themselves very monolithic, such behemoth, completely against this idea of agility and iteration, and that's what we need to change. And I don't have the answers. I'm working with the American Medical Association on how do you revamp medical education in the United States, given that AI is upon us. And I told them I don't have the answers, but I know that we need to involve people who don't have backgrounds in medical education to be able to overhaul medical education.
Thank you. Thank you, guys. We are moving on our last session. I would like to invite Dr. Geert Meefert from the Leuven, Belgium, to give us a talk on when is validation sufficient for clinical use.
Thanks. Maybe I'll first start with saying I don't have the answer to that question. So I'm going to give you some ideas, but there's definitely not a final answer, and there's maybe several dimensions to that question. I have no major disclosure apart from that I'm trying to validate and clinically apply two of the AI applications that we've developed in my research group. One is concerned with TBI, the other one is concerned with acute kidney injury. Artificial intelligence is a great invention. As somebody who's been working on it for the past 15 years, I can be maybe a bit skeptical about it as well. But I think the quote by Jerry Seinfeld made in the Tonight Show a couple of months ago is absolutely great. So we're smart enough to invent the AI. We're dumb enough to need it. I think that's also the point that Leo Celi made. But also so stupid we can't figure out if we did the right thing. And maybe that third dimension is concerned with validation, because we should realize that artificial intelligence is not artificial and also not intelligence. Basically, they're huge probabilistic systems and models. And as with all statistics, we should be very skeptical about how we validate it, especially if we will base important decisions upon these systems that may concern the lives of patients. And now we see in a lot of fields in medicine, we see that these applications actually are being applied, that they've not only been developed, but they're actually being applied, and that they work in clinical practice. In radiology, pathology, dermatology, ophthalmology, name it. There's a lot of fields in medicine who actually already work with these systems. And the ICU being a data-rich environment, has always been hypothesized like this is the ideal environment for AI to work. I mean, this is what this whole session is about. So the ICU should be the place where we can use these AI systems, because we have a lot of data, we have a lot of smart people, we have outcomes, and so we can apply them. And this is actually to me, one of the best papers on AI of the past years, which is actually a graph on the technology level readiness of our current AI systems. And we're together with the group of Rotterdam, they invited me to participate in an update of the paper, and I must tell you that we're not much further than this. So these are the number of papers that are published. The larger the circle, the more papers, and this is a technology readiness level. And as you can see, most of our models that we currently use and publish are at the level of model prototyping and model development. A lot of papers. Model validations, not so much paper. Real-time model testing, even fewer patient. Workflow integration, almost no paper. Clinical outcome evaluation, almost no papers. And I think this is a problem. I mean, we cannot continue to be stuck in this phase. Even while we're all very enthusiastic, we should go into that direction. We should go into the direction of real-time model testing. So there's a validation gap and there is an implementation gap. Now, when it comes to validation, I mean, this is very difficult. We don't have the 15 minutes time to explain all of that, but I will give you maybe a simple example. This is a model that we developed almost 10 years ago, a model that can predict acute kidney injury in the first week of ICU stay, the AKI predictor. And the model uses clinical parameters at baseline, at ICU admission on the first morning and after 24 hours, and will predict that risk. Now, if you develop these models, you have a database. We had a database of a previous clinical trial, and then you try to find what your best model will be. What is the ideal model, and how do you do that? You do some internal validation, and that can be a split sample. You can say, I will split my data set in two, and then I will develop on one data set and then validate on the other half. This is maybe not the ideal way. For this, you would need a very large data set. So what people typically do is cross-validate. They develop, for instance, on 10. They develop the data set into 10 boots. They develop on 9, validate on the 10th, and then you can repeat this process a couple of times. Or you can do bootstrap, where you just continue to mix the data set, typically 100 times or more, and then you test performance on the other bootstraps, and then you get a distribution of how the model works. And so this is what we did with our acute kidney injury model. So we did that, and then also typically, if you see people presenting their models, they're always very happy when they can present a nice a rock curve, a nice area under the curve, but there's obviously more dimensions to that. So this will tell you how good is my model in determining the outcome or not, in this case acute kidney injury within the first week or not. But you also need to know the calibration, very important. Is this model actually suitable for the data set, for the data set I want to use it to, especially if you move to new settings, other settings, so very important. So don't only look at AUCs, you have to look at calibration, and it can happen that an AUC is very good, but that calibration is totally off, which means that you cannot use the model in your data set. And then third, which is a third dimension that is rarely assessed, is clinical usefulness. Is the model actually useful? I mean, is it in the risk thresholds that it predicts? Does it actually add something to what I would normally do? Does it add something to what if we would consider all the patients having the same outcome, or what if we would consider none of the patients? So you would need some calibration benefit, and for instance, decision curve analysis can be a good tool for that. But of course, it doesn't stop there. Then you go externally. And so what we did with the acute kidney injury model, we actually we did a prospective study, compared against doctors. I will come to that later. But it was also externally validated in another large retrospective data set, and which is always nice. Other groups used it as well, and have validated it in their setting. So that is really nice. When you talk about AI, you tend to have to update your presentations all the time. So we've seen the OVIS study presented in the opening session, a JAMA paper, really nice paper, I think a fascinating model, but here as well, we're still in the setting of validation. So we have still need to wait for real-time model testing, even for this model. And I'm hoping that this will happen and that, of course, it will succeed. We are working in Europe, so if we are working in Europe, we have to work with European regulations, and if you want to validate or test your models in a real-time clinical setting, you're bound to the legislation, which is the medical device regulation. And as most AI systems are medical devices and will be considered a class 2, either class 2A or class 2B, which means actually that they're considered to be an potential intermediate risk for these patients. And which means that you have, in your study, you have to make sure that this risk evaluation is done when you set up the study, but also it involves some obligations when it comes to follow-up. And for instance, we were unlucky enough to start our validation of our traumatic brain injury model right after this MDR regulation went into action. And actually, nobody knew precisely how we should do it, so it took us more than a year to get this study registered, which is now ongoing. We're currently recruiting patients, but it does mean that you have to apply to your local regulatory agency, to your national regulatory agency with your study, and that it has to be approved there. Then the second piece of legislation in Europe that you will have to comply to is the AI Act. And the AI Act is different than the MDR regulation. What is the AI Act? The AI Act is actually mainly concerned with preventing potential discrimination, so guaranteeing the fairness of what you do. So the MDR Act is about how the device works and what is the risk for the individual. We can say here it's about the risk, maybe say broadly, the risk of the population where you want to apply to. So will it treat every subject in a fair way? And knowing that most AI models are learned on data, and this is true also for our clinical data, of course, it will reproduce existing biases in that data inherent. So it's not necessarily via the algorithm, but more in the data that are used to generate it. And people often say, well, then you add more data, but that won't solve it if these new data sets that you use are built on the same biases or have other biases as well. And so for that, I think it's important to be very critical about your data, very critical about your data set, and that's why data science has the term science in it. It's not just throw an algorithm to a data set and see what comes out of it. And actually, if you ask artificial intelligence if it is biased, it will be very, very honest, and it will answer to you that it is biased. So I put this question to ChatGPT, to what extent are you biased? And it says, as a machine learning model, I'm trained on the data that is provided to me. If the data is biased, that bias might be reflected in my responses. However, the creators have implemented some safe rails to prevent that, but it's still possible that some biases still exist. And it's important to be aware of that. And it's very clear, even now with image generation, if you put a prompt in DALL-E or in FreePic AI and you ask for a doctor, this is what you get. This is, and if you in the same prompt ask for a nurse, this is what you get, right? So I think it's clear which bias is in here. There's clear gender bias in there. So clearly, in the data that are around, there's more male doctors that are presented as an example and more female nurses, even while this doesn't reflect reality or doesn't reflect society as we would want it. Same here. These are clearly this was the search that I put in, and you clearly see that these are all people from same contact with the same skin color, which does not necessarily represent the whole group of poor persons in the world. So bias is in the data, and algorithms will continue the patterns that you show them. So if you show them a bad pattern, they will echo a bad pattern. And so you have to be aware of what the decisions were made when you collected the data. And bias is when somebody is really systematically off mark. So bias has nothing to do with variance, because variance can exist, but bias has to do with results that are systematically off the mark. And for instance, the mimic data set, which is great and which a lot of us use to develop our models, has been known to be biased as well. And so this is a paper of 2022 in Nature Scientific Reports that have discovered that there's actually bias in treatment and data representation, that there's disparate treatment in mechanical ventilation based on ethnicity, gender, and age, that there's underrepresentation of certain demographic groups. And so, which means that if we train models on this mimic data set, what a lot of people do, we have to be aware of that the data is not perfect in that sense, and especially if you will then validate them only in that data set, you have to be aware that it might not necessarily apply to your context. Eric Topol, who is a great visionary and who really embraces the AI revolution, published a great Nature Medicine paper on that, which I think is still actual, who actually says that, look, we really have to study the application of the AI models in clinical practice as well before we start using them. And of course, how can you do that? Because what do you do? And traditionally, and we made the mistake as well, these are two models. One is the AKI predictor that I told you about. This is a model to predict cardiac surgery discharge. In the beginning, we made the mistake that we said we want to beat the doctors somehow. So we want to make them better than the doctors. Well, I don't know if that's necessarily something you would have to prove. I mean, what we usually prove is that the models are as good as experienced doctors, which is good for the models, not a surprise. But does it really help us to have something that can do what we can do? Well, maybe we are better helped with something that will improve our workflow, for instance. And this is a study, this is actually a great study where they used a deep learning network to protocol CTs. And they were not that much interested in the accuracy, but they were interested in how this would improve the workflow of the doctors. So if a radiologist had to see 100 CT exams on a day, it would simply present the ones to him first that would probably show something, such that he could increase his efficiency, and that is what they targeted the study for. So they targeted prioritization rather than classification, and that made this model such a success. So, to conclude, I think there's a lot of challenges that are there. There's a challenge of external validity and bias, and so we should be aware of that. There's data quality, inclusiveness, and whether the outcomes are patient-centered. We should, I think, focus, if we test them, these models, we should focus on human interaction. We shouldn't focus not necessarily on improving an AOC with 0.1 points, but whether it actually improves human interaction. The same like, I mean, I can read a map and I can get somewhere, but a GPS system just makes my life easier. This is maybe how we should look at them. And then in the end, this is the way, I think, to build trust, and I think the trust needs to lie with us. We have to trust the system, but also our patients. Our patients have to be reassured that they will actually benefit when we use these tools. And with this, I would like to end my talk. Thank you. You do the questions at the end?
Correct. Yeah, we should have one more talk, and then we'll have opening for questions one more time. So I get the privilege of introducing our last speaker. We'd like to invite up Ari Erkol, and he's coming to us from Cambridge in the United Kingdom, and he's going to speak to us on making digital work, safe implementation of new technologies in the ICU.
Yeah, thank you for the introduction. Thank you for the invitation to come and speak. Great pleasure. So I'm an intensive care doctor. I've been an AI researcher for, since year 2000. I built my first ever AI models, a natural language processing model for analysing pathology reports and a Gaussian mixture process for looking at immunophenotyping from flow cytometry. And I've continued to be interested in developing algorithms and shaving bits off AUCs and so on. But more recently, I've become the Chief Clinical Information Officer for my hospital, which is a large academic centre. And so now it's my responsibility to introduce and deploy AI solutions and other digital technologies, not just in the ICU, but across the whole hospital. And so I'm going to give you some insights, I think, that I get from that, because it's one of the things I have to own is thinking about what the safety is and how we do these things in a meaningful way. So, sorry, we'll just go back. So the caveat, I'm going to begin with the regulations vary around the world. I'm going to take a EU and particularly UK standpoint, but mostly an EU standpoint. And I'd like to begin just by giving you this sort of slightly provocative statement that the coolest, smartest, best performing, most revolutionary, most novel medical AI thing is utterly useless if it doesn't change clinical practice in a beneficial way, of course. All right? And the second thing that you need to know is that you can't just deploy this cool AI thing, whether you've built it yourself or whether you've got it from a company, and expect it to be legal, safe, useful, or to actually be used by anybody. Right? And that's what this talk is going to be about. What I'm not going to talk about in this talk, because it's been much better covered by Hed and Leo earlier, is bias, accuracy, all these drifts and all these things that are also incredibly important. So chapter 1, which is contact of your cool thing with the enemy. And the enemy, as Michael Pinsky sort of alluded to earlier, is the doctors. Because doctors, and actually clinicians generally, we do not follow the rules. We are unreliable. And that is a major problem for deploying technology. And hopefully I will convince you of that by the end of this talk. So here is it's not AI, but it is a risk tool. I wrote this in a spreadsheet a couple of nights ago after a couple of glasses of wine. And it's a Chad's Vask risk score calculator, and you can put in the things. It's got drop downs and stuff. And you could do this as well after some Belgian beer this evening, and it'd probably take you 10 minutes to write such a thing. And then you could put it on your computer in your ICU or in your hospital, deploy it, and people can use it. And congratulations, you've just created a software as a medical device, and you've just broken the law. Okay? So we just need to understand that, and that regulatory framework exists for very, very good reasons. And one of the things that you need to think about, not just about breaking the law, is also how is this thing going to be used? So is it safe? Is it being validated? Does it have a CE marked or whatever the things? I'll talk about it later. But also, is it going to be used properly? So this is a study that's been shown several times in several talks over the last couple of days. It was a deployment of a pop-up. It's not AI. It just pops up and says, I think your patient may be developing acute kidney injury. Do you want to do something about it? In your electronic medical record. And yet, so it seems fairly benign, but in fact, it was associated in non-academic centres with an increase in really quite clinically significant increase in mortality. Now, why is that? Well, one can hypothesize all sorts of different things. But the thing I really want to get across to you is the most simple thing that seems really, really obvious can have very, very unexpected implications when you deploy it in the real world because of the way people use them, the technology. And it isn't just about the technology. So this was a paper, one of the few points on those graphs that here showed earlier of a piece of technology that was taken all the way through to randomized controlled trial. Sepsis prediction algorithm, actually really quite impressive, absolute risk reduction of 12%. So impressive piece of machine learning. But in fact, when you start looking at the methods in the intervention group on receiving an alert, right? So there's an alert associated with the machine learning model, which there wasn't in the placebo group, in the non-intervention group, I should say. And so is it the incredibly clever machine learning model that has a fantastic AUC and is validated, whatever, or is it just the fact that there was an alert and, frankly, just any kind of early warning score could have worked? You've got to think about the system as a whole that you deploy the technology into. Okay, so this AI kind of medical practice human interface is really, really complicated because medicine is a really highly regulated industry. I'm regulated, you're regulated, drugs and therapeutics are regulated. If your AI model, one you've built yourself or one that you've bought, misbehaves, then your patients may die or be harmed because you misdiagnoses or you make the wrong treatment decisions or triage wrongly. Or you may worsen healthcare inequalities for all the reasons that Leo went through earlier, because of the biases that may exist in software. If your software misbehaves, so not your model, but your software that you deploy it in misbehaves, it may not be available when you need it. It may break down, right? Or it may expose the rest of your hospital to a cyber risk threat. So that's another important concern. And if your doctor, and I mean healthcare worker really, misunderstands the output of the model, they may use your AI model for a purpose that it was not intended and maybe unsuitable for. And these are all important considerations, and they really happen in the real world. So I want to think a little bit about what a medical device is, and there are different definitions that are out there, and the medical device regulations are not absolutely specific, but broadly speaking, in the data sphere, software as a medical device is anything that takes clinical data and does anything other than just filing it. So an electronic health record, in the broader sense, is not a medical device because it sort of files data. But does anything other than filing the data, manipulates it in some way, and then produces an insight from that data that you then use to change your clinical management of something, right? So that is software as a medical device. And what a lot of things follow from that, a lot of scoring systems, a lot of symptom checkers, a lot of different medical calculators and algorithms follow as being software as medical devices. So we're going to think a little bit about what that means for us. So chapter 2, software as a medical device. Okay, so any software that processes data for medical purposes is a medical device, and there are laws that define how we use it. And the laws in the US are somewhat different, so let's stick with EU. Now, if you go and buy a product, you will find that it is CE marked. And it's very important just to understand what CE marking means. In fact, it must be CE marked. What CE marking means, it does not mean that when you deploy this product, that it will be safe. It does not mean that it will make patients better. It does not mean that the product, combined with the way you use it, will not even harm people. What it means is the product, as Vitaly said earlier, will do what it says on the tin. Right? So if this was a hairdryer, then it says one of the specifications is that it will not electrocute you. Okay, under normal use. If you use the hairdryer to try and warm your bathwater up, then you are not using it for the purposes that it was CE marked, and therefore, of course, you may be electrocuted from it. And exactly the same thing applies to CE marking and regulation of software as medical devices. There is a use case that it was envisaged for and developed for. Hopefully, it was properly validated in that use case, and a certain set of performance criteria were drawn up and demonstrate that it works. But if you deploy it and do something else with it, or as a result of the insights, some other things happen that were unintended, that's on you. Right? And actually, unfortunately, now with AI, with the AI Act, the other piece of the EU AI Act is also on your hospital, because your hospital now has, or the healthcare provider system, has some regulation that requires it to monitor what's going on in the future. So that's what CE marking means and does not mean. It costs about probably 250,000 euros to CE mark something. I mean, it's a ballpark figure. It's quite a lengthy process. If you want to know a little bit about kind of how that works, then this is the document to look at, the regulation EU 2017 on medical devices regulations. And there are, as Geert showed earlier, a number of different classifications depending on the risk of the different devices. So high risk, class 3, sort of invasive type things, down to class 1, low risk stuff like slings and so on. Now, this is nothing new that you can deploy devices. Here is a medical device. It is an esophageal Doppler, so you might remember those. And you can deploy it in a system like this, where you optimize your stroke volume if the patient looks fluid responsive. It is CE marked, it is safe, it will not electrocute you, but if you deploy it in this randomized control study, it actually was associated with detrimental effects in the primary outcomes. More bowel edema, more dilutional anemia, and so on. Completely safe, you can buy it, but actually when deployed in the system, it's bad for patients in this way. We've seen this diagram already. We mostly work in critical or serious situations, which means that whatever happens, we're going to be in the higher risk categories of medical devices when we're deploying bits of software or actually anything in the intensive care unit. Now, where does this leave you as people who might want to deploy your own bits of software or your own devices or your own software as medical device? My Excel spreadsheet that I showed you earlier. Well, it is possible to do that. Article 5, subsection 5 of the Act, I won't show you all of it, does give an opportunity for you to self-register without going through a whole CE marking process to a particular medical device, including software as a medical device. And there are some preconditions, however. One, is that no other device must be available. So you can only do it if there is literally nothing else on the market that will do this for you. So that's the only that situation that you are allowed to actually deploy your own thing without CE marking. The second thing is that you must not give it to anybody else. So you can deploy it locally, but you can't start marketing it or give it to your friends in a different hospital or somewhere else. The third thing, which is really, really important and was mentioned earlier by Paul Elbers, is that you have to use a quality management system. And I'll talk a little bit about what a quality management system is in just a second. So there are a number of bits of regulation you might also want to look at. What defines a quality management system, how you actually build a piece of software, is an ISO standard, ISO 13485, which is a standard telling you about medical devices and QMSs. But you also want to bear reference to IEC 6304, and there's another one at the end that if you are still awake, you might also want to have a look at. It's really those first two documents. And what they say is you need to work like this. And this will be really alien to us as doctors. This is what a quality management system looks like. Broadly speaking, what it says is you don't just build something and see how it works. You begin by working out what the problem is that you are trying to solve. In who? Right? So you very clearly define, a little bit like a randomized controlled trial, I suppose, you define which population I'm going to use this in and what do I want this piece of software to actually do? How do I want it to perform? So if you were designing D-dimer as a test to rule out deep venous thrombosis, you would be designing it to have a very, very low false negative rate. Okay, so that's what you're designing. Now, in reality, of course, you don't work like this. And the IEC and ISO guidelines do accept that, in fact, we develop something, see how it works, and then think about what the application might or might not be, whether it's good enough. But very important that you define what that application is. And then what follows from that is some documentation to actually say, well, actually, let's break this thing down so I understand how every little module of that particular system works so that I can test it, so that when a new version of Python or on your operating system, you upgrade from Windows 10 to Windows 11, that you can be absolutely sure that your piece of software will still work on that new platform. Right? You know which bits you need to test and which bits you don't need to test. So that's how you have to do it. Otherwise, you may not deploy these things outside of a research study, I should say. So the next thing to do is a clinical safety analysis. This is a UK thing, but actually the EU AI Act makes it incumbent upon us to do something very similar. And it's very good practice anyway. What the safety analysis is to think about what this is. You've got your model, you've got your software thing, you've deployed it. What are the safety risks that will happen in deployment? Right? So, for example, what happens if the thing stops working or isn't available? If it's mission critical and you're reliant on it as deployed, you may harm somebody. How will you mitigate against that? What about if the model becomes out of date? You have to monitor these AI models in case it has drifted. How will you do that? What if your model suddenly doesn't work as expected? What is the likelihood of that? What are the likely consequences of that? And how will you mitigate it? I do this a lot in my hospital. Here's a real one. You can see sort of software given invalid data to interpret, CT scan, and then we risk score. And think about, actually, how can we reduce those risks with mitigations to an acceptable level? Okay. And then we signed off, and there's a sort of set paperwork process. And it's the usual kind of matrix of the likelihood of something happening versus compared against the impact of something happening. So the last thing I really want to talk about is adoption. And this is the most difficult thing. Because you might be very, very keen on your AI thing, and you might think it's really cool. But it's the clinicians that are going to use the technology, right? And they need to change what they're doing. And that adoption is a really clear stumbling block. Because just implementing something, just putting something out there will not work. You have to train people, you've got to reimagine the workflows to make best use of the AI, and then you've got to hopefully demonstrate some benefits as well. So you need, in order to do this, individual, organizational, and operational buy-in. Otherwise, people will simply not use it. There are lots of models that I will point you to about why bits of technology don't get adopted. The one I quite like is the NASCAP framework, but there are others out there as well. But it's really, a lot of it's about thinking about what is the value proposition for the individual that's going to use it. So we do electronic prescribing in my hospital. There will never be a user interface that is as simple for me as a doctor as a piece of paper where I scribble something illegible on and throw it vaguely in the direction of the nurse. Okay, so the value proposition for me for electronic prescribing is not great. So, but it's a matter of getting that across. So there's a clear stumbling block there for me to adopt that technology. And it's trying to understand and get inside the minds of the people that you're trying to get to use the technology. As an example, at Cambridge University Hospitals, I surfaced about 500,000 interruptive pop-ups, like that one, for example, that made mortality, that seemed to be associated with worse mortality, every single month to our users. And you've got to be very careful that what you do doesn't just contribute, I don't know if people may be old enough in the audience to remember this, to something that's just an irritation, because if it's an irritation, it's not going to make any difference and actually might make things worse. And it's always about technology, people, and process, right? The technology is just one part of it. You've got to think about the people and how it's going to fit into their process. The last thing I just want to say is, how will this change stuff? So I'm just going to dwell on this for just 30 seconds. There's something called the productivity paradox. This was made popular by Robert Solow, but he wasn't actually the originator of this. What is it the case that IT makes us more productive, that makes us able to deliver more healthcare? Well, we don't know, because we don't yet have enough data, because we've only been digitised for quite a short period of time in healthcare. But if you look in other industries, look at the economics of other industries where IT has been brought in, and think about whether or not it improved productivity, it allowed us to do more stuff, make more widgets, in our case, see more patients, treat more patients, more illness. Actually, the answer is really mixed. It is marginal at best. And in the service industry, and we are a service industry, it's really, really questionable whether technology has ever made anything any better. And yet, that can't be right? Because industry's not stupid. They've got to spend, there's a bottom line at the end of it, and yet we see technologies everywhere, right? We see technology, we see computers in everywhere we go. So, what is it that technology actually allows us to do? Well, it doesn't necessarily make us more productive in itself, in and of itself. But what it can do is it can allow us to be more scalable, which we couldn't do with the current, which is not the case with medicine at the moment. And what it can do is allow us, with a given workforce, if we design things properly, to produce a wider variety of products. And for healthcare, read different kinds of treatments, or nuanced treatments, or precision healthcare. That's what it can do, but it doesn't do it on its own. And in the turn of the last century, last but one century, when electricity was introduced into the mills and into industry, it took 20 years for that to actually show benefits in terms of productivity. Because initially, it was just solving an incremental change in, I'm quite busy with this will make this easier. It takes the radiologist a long time to read this will help radiologists read it. If we really want to see the benefits of technology, and I firmly and truly believe there are technology, it's us that we need to redesign, and we need to think about how we actually change our systems so that we can use the technology better. Jeff Bezos was not selling books out of his back room with a car, distributing things locally, and then got a computer, and suddenly Amazon happened. It was a complete reimagination of how sales could work on the basis of the opportunities from a piece of technology. So, in summary, implementing AI, machine learning, digital things is really hard. It's not just a matter of buying it and turning it on. There are regulations, there's safety, and there's adoption, which is really hard. But the last thing I would say, as digitally aware clinicians in this audience, you are the only people that can do this and affect that change. Thank you very much.
Great. We'll invite Dr. Mitford back up, and we will open up for questions. We have about 9 minutes left. I'm going to see if there are any hands in the audience. There is one. Okay, great.
Thank you very much for the talks. Hello. Hi. Do you think we maybe, because we've said the word AI, lost our minds here? Because if we just said statistical prediction model or stats, would we be hand-wringing in this way about validation? Because when I was an intern, I could pull up a Glasgow score and a Ranson score for pancreatitis without wondering if I was being biased or having too much privilege. I could just use the score, and I didn't have to do what the score said. So obviously, outside of medical technology, medical devices, obviously that has to be regulated. But for local prediction models, isn't this impairing our ability to do exactly what Leo Celi and all this wants us to do about trying to deploy correctly and tune on our local populations? It's making it impossible for local hospitals to actually make the models they want if they have to go through these crazy processes and then validate.
So that's a great question. I get asked this sort of thing quite a lot. I have to say, overwhelmingly, because I've seen things go wrong, actually having some oversight of what's going on is overwhelmingly a good thing to do. It's actually not that onerous. If you are designing your own model from scratch and actually want to implement it, yes, it is onerous. And I think we also have to take a somewhat pragmatic view, and bearing in mind it's case law, so we'll see whether we'll get sued or not in the future, whether we end up in court. We have to take a certain pragmatic view as to whether my CHADS-VASC score really is something we want to go through a quality measure. Do I need to see mark my spreadsheet or not? But nevertheless, if you look at actual implementation of AI solutions when you get them, most of them will allow or should allow you to fine-tune, and you should. And in fact, the AI Act insists that you must validate it on your local data. So we have to just build that into our process of when we get a new thing, that we just validate it on our data. But as you say, none of this is new, but none of it is good either. So I know that in my intensive care units, in my adult intensive care units in my hospitals, over the last 5 years, we don't actually provide cardiac, I should just say, we have spent £150,000 on B-natriuretic peptide tests. Now, B-natriuretic peptide is a test that was developed. It has fantastic statistical properties if you are a primary care physician or a cardiologist in deciding whether your heart failure is getting any worse, whether you need an echo, and whether you should be admitted to hospital. And there are protocols that are evidence-based that go behind that. I do not know, and I keep pointing out to my colleagues, what the normal range is for B-natriuretic peptide in an intubated, ventilated, septic, hyperalbuminemic, noradrenaline-soaked patient on a ventilator. I don't know what that normal range is. Well, I do, because I've looked at it, and guess what? They're all in heart failure, apparently. And yet we are using that. Now, does that really matter? I don't know. But we are doing this all the time, using things for purposes they're not intended. And you can imagine, like with the with the esophageal Doppler, that we may end up doing harm. So we should be thinking in these terms. We should be thinking critically about all technology that we implement.
Thank you for the presentation. I have two questions. First, about biases. The biases that we see in the LLMs are basically from data. There's bias in society. So when developing a clinical decision support tool, is it our duty, task, to rewrite that through the opportunity of AI right now? And to what extent? That's the first question. The second question is, when I hear everything, all the regulations, all the clinical trials that we need to do, and the prediction of the last speaker that, or the example that 20 years it took for electricity to have impact, what's your prediction for this technology to have impact in our clinical lives?
Well, bias is a bit unavoidable because it's in clinical contexts, we know well that there are certain groups who get less access to healthcare, who do not end up in the ICU. So there's racial and gender disparities in the patients who actually end up in the ICU. So there's an immense bias from the beginning. I don't think we can avoid it. I think we should be aware of it. And that's maybe, if I may, the remark or the comparison with a lab test. We don't do yes-no decisions on lab tests. So we just say one element of the clinical picture of the patient is that lab test, and if it fits with the rest, we can put our treatment in a certain direction. And maybe we should think about AI the same. I think we give it too much value. I think it can point us in a certain direction, but it will only be a part of the puzzle. It will not solve the puzzle. It's a part of the clinical puzzle that we have. If it can improve our efficiency, if it can draw our attention to certain things, it's good. But it's not that it will replace. It's not an artificial physician that you can just throw your patient, your EMR to, and then it will give you automatically the answer of the therapy that you need to use. And I think that's the way we need to think about it. And I forgot your second question. Sorry. What was the?
The second question was about how do we get to a new world, not in 20 years. Maybe I can have some comments on that. So I don't know whether this is possible, but I hope so, because in less than 20 years, healthcare will be overwhelmed by the demographic changes that we're seeing. So we better move fast, and we better be better than electricity. So how do we try, and also, AI is coming whatever happens, right? So we want to try and make sure we land in the right zone as much as we can influence it. But I would encourage you just to think differently. If you've got a system at the moment that's a bit crappy, digitizing a crappy system will end up with a crappy digital system. Okay? You've got to think about how do we totally redesign things. So one of the things I'm looking at the moment is some using large language models to automate message responses to patients. So it just drafts a message response and allows, and hopefully, we will see, right, whether it's quicker for people to just review the message and then write back. Why am I doing that? I'm doing a particular service that actually uses a lot of messaging with patients over our clinical portal. Of course, I'm very interested in that service. If I can make that service better, that's a great thing to do, but it's an incremental game. What I'm really thinking in the background, and I don't know whether this is going to happen or not, is if I can speed up replying to messages, then can I have a completely new model of care where for the right service, we don't take patients into hospital at all. We don't look at them in outpatient clinic. We keep them completely at home. But we open up two-way messaging all the time, which would be a floodgate. We don't want to open those floodgates now because we would be completely overwhelmed. But maybe, if the technology works, then there's a new model of care because we can actually deal with the volume of these things. And that's the way I would encourage you to think. Not just, how do I employ this to an irritation in my current workflow, that may be very well worth doing, but also, how can I change the whole workflow in order to maybe make use of the technology advantages, possibly?
Thank you. Hello, my name is Mihir Sheth. I'm an engineer from Oxford University. So, hello from the other town, Ari. I think you just hit on a really interesting point right now, which is that in order to improve uptake for AI, the design of it needs to be really good. And I think that's something that's often forgotten in implementation and in designing. Generally, when it's done by engineers, it's not done well. I'm more than happy to acknowledge that. So how can we promote that? How can we promote engineers, designers coming into the hospital with doctors and not being seen as outsiders who are trying to take away their jobs or quote unquote know better than the clinical experts?
That's interesting. So great to have an engineer and maybe other engineers or similar in the audience. So let me just speak your language for a moment and tell you the first thing you need to understand is that healthcare, and I think you'll love this, is a complex adaptive system, right? Now that might not mean anything. What that means to everyone else is there are a lot of moving parts and they interrelate in a really complicated way. And if you change this thing over here, a little bit like the immune system, right, then actually the system tends to respond in a way that it maintains its equilibrium and nothing else really changes. So from an engineering point of view, what you need to come in order to make your product really work is you need to think about that. And you think about actually what are the key nodes in this system and actually do the system mapping. Because doctors generally won't do it for you. Right, and the system mapping really is the first thing to do, the process mapping. And what you will find is actually quite often there are things in there that will be optimizable quite simply because they're just a lot of variants that really, when you dig in, doesn't really have to happen. So you go in with that, what is the big picture? Let me understand the big picture, open mind, ask questions about, okay, well, your system is that John does this when it's busy, but Jill does that when it's not. Why is that? And try and get some data out there. So I think that's the first thing. I think the second thing really is not advice for you, but it's advice for everybody else, is that you need these people, right? You have to, for the healthcare professionals, we will not do it, and the engineers will not do it. We will do this together, right, along with some healthcare economists and also other people probably as well. So please keep coming to these sorts of sessions and hear people like me, I know I'm between you and lunch, talking about some of the language that you need to think about so that you can we can, as a group, have meaningful conversations with our colleagues in other disciplines, because that's how we will redesign, and I hope that's how we will deal with the absolute, sorry to worry you, but the absolute tsunami of healthcare requirements that are going to hit us in the next 5, 10, 15 years.
Thank you. Now AI is standing between you and lunch and me and the warm place. Thank you so much. It was a great session. And we are always available via email and social media.